Okay, everyone, welcome to our MathSoc and ELSOC collaboration on MATH2069 or MATH20 revision seminar. Hopefully this will help you to prepare the finals. And yeah, let's begin. Of course, in MATH20 we have two topics, so complex analysis and vector calculus. We will start with integration part of complex analysis. And yeah, but before we do that, so MathSoc just like to make an announcement to say we have PM entry program running next year. So this is an excellent opportunity to just meet and help first year students. You know, we have all struggled in the first year, and just help them to do stuff and also help us to build up connections and just bond. Yep. Oh yeah. So yeah, we'll give you a minute or so to scan the QR code if you're interested in it.
Just make sure when you go back and tell them that we're only doing the last 4 weeks.
Yeah, sure. Okay. All right. So let's begin then. Since we have already done weeks 1 to 4 in our midterm crash course, so this crash course will mainly focus on the second half of the syllabus, which I guess is the more challenging half. So starting with the integration. But to do that, I'll just quickly recap on what's in week 5. So integration in complex land, as we know, is not quite the same as what's in real numbers. What you integrate is along a curve. And what a curve is, it's basically a function that's being parameterized by often t. And initial point of the curve is gamma a, and the final point of it is gamma b. Range of a curve is just range of the function. So like what we have done in 1a, 1b applies here as well. And the curve is closed if the initial point equals to the final point, or just gamma a equals to gamma b. And it's simple if it never touches each other. So for example, if you have a curve like this, it's simple. But if you have a curve which intersects itself, let's say this, it's not quite simple because they touch each other here. And in our syllabus, we're usually more interested in simple curves. And those are just different types of arcs. We have went through this in midterm crash course as well. So an arc is just similar to a curve, but those are different types. Polygonal path, basically we can construct it using a finite number of polygonal lines, so straight lines like this. And a closed polygonal path is just a polygonal curve that's closed, so initial point equals to final point. For example, I've started here and then ended here. And this curve will be simple because it doesn't cross each other. Yeah, so similar to what a curve is. But before we go into actual integration, it's better to take note of those two parameterizations, which will be helpful in lots of integration, which is a parameterization of a line and parameterization of a circle. The first formula, which is a parameterization of a line, it should be familiar from high school because this actually represents the internal division formula. By letting t to be all real numbers between 0 and 1, we basically construct a line which connects z0 and z1 like this. This is a line. And the second parameterization basically parameterizes a circle of center z0 and radius r. Yeah, so it's worth to memorize those two to just help in many of our integration tasks afterwards. And yes, so as we will see later, often we're more interested in integration along a contour because, well, I'll explain this later, but what a contour is, it's basically an oriented range of a smooth curve gamma. So a gamma is a function, right? So we could go from like very fast, then very slow, and then very fast again, depending how we actually parameterize the curve. But contour, we don't worry about this. We just look at the range of it. For example, in this case, well, we just care, okay, this is a line. We don't care what happened in the line, whether it goes fast, slow, or if it shuffles back and forth. Yeah, so that's basically what a contour is. And if I have a closed contour, we usually describe its direction by anti-clockwise or clockwise. And the standard orientation is usually anti-clockwise, so like this. as we will see later. The nice thing of complex integration is that it's analogous to basically real integration, especially when we're integrating with respect to a real variable, like here. Just take note that t is a real number. When we're integrating with respect to a real number, what we can do is we split the integral. For example, if we want to integrate from a to b, x plus iy, and we're integrating with respect to some real number t, what we can do is we just treat I as a constant, similar to like other numbers like 1, 2, 3, and integrate each part individually. So yeah, this makes integration with respect to a real number pretty simple, and it has surprising applications. So since it's analogous to real integrals, all those properties from real integration also carries over to complex n. For example, we can, sum of integral is the integral of sum, and that we can just pull out any constants outside the integral. And we can also do integration by substitution or reverse chain rule, as many of us know it, and integration by parts, and this inequality here we have seen in Math 1a. They all carry over to complex integration. So yeah, complex integration, just treat I as a constant and do whatever we do with real integrals. So let's look at this example here. Integral of 0 to 2 pi of e to the power of t cos t dt. Well, it might be tempting to do by parts, right? Because that's how we have been told it in Math 1b and all of high school. But this question could be made much easier if you just consider cos of t equals to real of e to the power of it, as what we have done here, and just make it into this integral over here. I hope we can see why is this integral much nicer, because we can combine e to the power of t and e to the power of it by using index laws. So yeah, it becomes this. And this is just an exponential function, which is much easier to integrate. And we just integrate and substitute in the 2 pi, and we have this thing afterwards. But remember, we have just e to cos t is our original integral, so we have to take the real parts when we do just consider the integral with e to the power of it. And once we equate the real parts of both sides, we have e to the power of 2 pi minus 1 on 2. Yeah, so this method doesn't require by parts and just allow us to integrate much faster. And as we shall see later, this is how we often integrate trigonometry, convert it into exponentials. And what you have seen before is integration with respect to a real variable. When we're integrating with respect to a complex variable, for example, z over here, it's not going to be as nice, but we can convert it into a nice integral with respect to a real number, a real variable, by just parameterizing z equals to gamma t, where gamma is the curve in which we're integrating on. And what you do is similar to integration by substitution. Like, it's similar to this, although it's not quite the same. But yeah, I personally find that helpful to remember this formula. Like, try to make this integration by substitution style. And after that, we have seen how to integrate this before. And due to this parameterization, we can convert it into an integral with respect to a real variable. So some nice properties also carry over. For example, the sum of a complex integral is the complex integral of a sum. And we can also integrate with respect to another direction. For example, if I have alpha, this is the alpha, right? It's just a random contour alpha. If we're integrating just in another direction, we don't have to do all the parameterization again. All what we have to do is multiply our previous answer by -1, and we can calculate the answer. And if gamma is the union of two curves, for example, this is alpha, this is beta, and gamma is the sum of them, or the union of them. then to integrate gamma, we can just sum the integral over alpha and over beta. So this is an example of complex sign integral. So we want to integrate z squared with respect to the unit circle. What you do is that we have seen before how to parameterize circles. So let me just scroll back to there. So I've seen that we can parameterize circles by doing this. Gamma of t equals to z0 plus by REIT, where t is between 0 and 2 pi. In this case, z0 is 0, right? Because, well, the center is 0 for a unit circle and r is 1. So in this case, the parameterization is just e to the power of it. And yeah, we can differentiate this curve to obtain I e to the power of it and, well, use our previous definition of line integral we have seen it's over here. By letting z equals to gamma t and times by gamma prime t. Now after the substitution, it's just rearrangement to become this. Again, this is the integral, which is pretty nice because we're integrating with respect to a real number, and the integrand is just, well, an exponential function, which is easy to integrate, and we can just use our reverse chain rule, which hopefully we have seen from 1a and 1b. So any questions so far with respect of integration? Right, cool. Let's move on then. So this is another similar example, except they gave us the parameterization, which is gamma t equals to t plus by I t squared. In this case, well, they help us by choosing the parameterization. All we have to do is to just chuck it in the formula. Differentiate the gamma with respect to t, we have 1 plus by 2it. And yeah, since t is from 0 to 1, that's our lower and upper bounds over here. And we can just substitute in our formula to become this. Substitute f of gamma t, or conjugate of gamma t, since f in this case is conjugate z. Substitute in here, and yeah, just rearrange and integrate it as what we do for a real variable, and we should arrive at 1 plus by ion 3. So this is a similar example, except we have to parameterize a line from 1 minus I to 1 plus I. As we have seen before, what you do is that we parameterize gamma of t by z of 0 plus by t, z1 minus by z0, where t is from 0 to 1. In this case, z0 is given by 1 minus I, plus by t of z1 minus by z0. So 1 plus I minus by 1 minus I, 2i. Yep, and so that's our parameterization. And just differentiate and chuck everything into this integral, and just integrate it as what we would do for a real number. So yeah, chuck it in, and rearrange, integrate. We get 14 ions 3. And some of you might worry, like, what if we choose the wrong parameterization? Well, we don't have to worry about that, because nice thing about complex integration is that our answer is independent of parameterization. For example, if I have z0 here, z1 here, we want to integrate along some arbitrary contour like this. Wait, let me just make the end black. We want to integrate along some arbitrary contour like this. There's like lots of ways in which we can parameterize this, right? We can even make it shuffle forward and back. But then the nice thing about complex integration is that we don't have to worry. As long as we found one parameterization, we can use it, because any parameterization will give us the same answer. So yeah, that's what this formula is saying. As long as it's smooth and both parameterization give the same range, then the answer they gave will be the same. And this is the ML lemma. So basically, M is the maximizer of f, absolute f. And the proof, well, I might just quickly give a proof. So we have integral with respect to gamma of fz dz. This equals to just some arbitrary parameterization of gamma. So f of gamma, but it should be gamma of t, but because gamma is a function of parameter t, but I'll just skip it over here. So f of gamma times by gamma prime dt. Oopsies, and yeah, we have seen before that this is less than ab of f gamma f prime dt. And this is actually just equals to ml by definition of m and l. So this is a pretty, I guess it's a pretty short proof, but this is a very useful property that allows us to do many things, especially in residue, which Thomas will talk about later. But before that, let's look at how we can apply this. Well, we have this integral over here, 1 z to the power 4 plus 1, and gamma is, what's gamma again? Okay, so it's a semicircle of radius r, so like this. Right, let me just draw the contour in black. It's a semicircle like this of radius r. So we want to show that this thing approaches 0 as r approaches infinity. What you can do is that we can just use the ML lemma. We will do this a lot during the real analysis part of complex analysis, basically like evaluating real integral. But what we do is we use the circular inequality, which is over here. Circular inequality. And technically there should be an absolute value here, but we can ignore it because we're making r very large, right? So we can safely assume that r to the power 4 minus 1 is, well, greater than 0. And yeah, just rearrange, we have this inequality over here. By using ML lemma, so the length of the curve here is just the length of semicircle, so length equals to pi r. L equals to pi r. We can just substitute in our ML lemma to obtain this expression over here, this inequality over here. And since we can make r arbitrary, like we did not specify r in any of the things we did before, right? So we can make r any number. If we make r very, very large, this thing approaches 0 from what we have learned in 1a. So this integral must also approach 0. So yeah, that's how we can apply the ML lemma. And the contour integral is, well, we have seen before. It's just integral along the oriented range of a curve, and it's independent of what curve we choose. Yep, so another thing that's very useful in complex integration is the Cauchy-Gaussat. So if a function, if I have any arbitrary contour, for example, I'll just draw some random closed contour, and the function is analytic inside and on gamma. So like f is analytic, it has to be analytic in the curve, but it also has to be analytic on the curve. So like you can't have some singularity, for example, here. If that's the case, then the closed integral is zero. And that's what we call the Cauchy-Gaussat theorem, the Cauchy-Gaussat over here. Another thing, it's basically saying, wait, it's totally next slide. Yeah, it's the next slide, so I'll go over that later. Let's look at this example over here. So gamma represents a unit circle. So method 1, we can let z equals to like gamma of t equals to e to the power of it, where t is between 0 and 2 pi. And just substitute and integrate. But as you can see, this might not be the most efficient solution. So a much better way is to use a Cauchy-Gaussat by observing this function. So let me just call it f of z equals to 2 of z on z plus 1 minus I we can see that this function is analytic everywhere except for z equals to 1 plus I. So let's just quickly label this on a Cartesian plane. Minus 1 plus I, it's going to be like here. That's 1, that's 1. And what you're integrating is along the unit circle, so like this. That's going to be 1, that's going to be 1. Minus 1, and that's minus 1. Okay, so as we can see over here, the function is actually analytic everywhere and inside the contour. So what we can include is that this integral must be 0. Yep, so that's one of the most powerful applications of Cauchy-Cossart. But another application of Cauchy-Cossart is that even if we don't have a closed contour, it allows us to do many things. For example, if I have z0, z1 over here, and the function, let it be analytic everywhere inside this, for example, random contour I have drawn, then integral is independent of the path we choose. For example, I've drawn 3 paths here from z0 to z1. As long as the function is analytic inside this contour we have drawn outside, then the answer is independent of the path we choose. So we can choose any path that allows us to integrate it more conveniently. And even better, if basically a function is analytic inside this contour, then we can actually find an antiderivative for it. Antiderivative, which is what we used to do for like basic real integration. So complex integration is now even more like real integration. F of q minus f of p. Well, and f is just any integral or antiderivative of f. Yeah, so yeah, which this makes our life much easier, as we can see in our next example. So we want to integrate this integral over here. So integral of 1 on z minus 1 dz. And what you're integrating on is, so minus I to minus I is going to be here, and minus I is going to be here. And we want to just integrate along some arbitrary contour which lies all in the left of the Cartesian plane. So I/z is less or equal to 0 over here. Yep, so in this case we see that there's a branch point at z equals to 1, which is over here. So yeah, we want to integrate this nicely. So if we just choose the branch of log z such that, so like arc of z, which we can always choose this, arc of z is between 0 and 2 pi, then the function will actually be analytic everywhere except for the black parts which I have drawn here. Since it's analytic everywhere to the left of the contour, we can just, well, use the antiderivative as we have seen here. So this integral is just, well, equals to log of, wait, let me just write it here. This equals to log of z minus 1, and I'm on minus I. Yep. This is just to say how we can choose the branch of log. We choose a branch of log that's analytic everywhere to the left of the Cartesian plane to just make our life easier to find antiderivative. And yeah, just after we have this, just substituting the I and minus I. And using the definition of log, we can just, well, just expand and gradually simplify. We should arrive at pi on 2I over here. So yeah, the trick is just to find an antiderivative which actually exists in the contour. And the nice thing about logs and arcs is that we can choose any branch as we want. Yeah, so while it's also a complex integration, the more likely type of question that's going to appear in your final is going to be some question which involve Cauchy's integral formula, which basically is an integral which is in this form over here. And the nice thing is that we can just integrate this without actually, well, integrate. So this is what we usually do. got the integral of fz on z minus w equals to 2 pi I times by f of w. So we don't actually just do integration. We just worry about what's this f of w and times it by 2 pi I. Let's look at this example over here. So we want to integrate e to the power of z on z minus 2 on z plus 2. So observing that they're actually unfortunately not the same form, right? Because we can only have z minus by some number at the denominator. But in this case, we actually have two factors of z minus something. But luckily, we have learned something in Math 1b called partial fractions, which allows us to convert it to two functions of e to the power of z on some, well, z minus a constant form, like this, like over here. And after that, we can use the fact that integral of the sum is the sum of integral, and the fact that we can pull any constants outside the integral to arrive at this. After we have obtained this equation, we can see that each of those integral is actually in the form which allows us to use Cauchy's integral formula. And yeah, this thing over here equals to 2 pi I f of 2. Well, I should have defined this. F of z is e to the power of z, because f of z, as you can see in here, is whatever that's on the numerator. So 2 pi f of 2, and this thing is 2 pi I f of minus 2. Yep, and just sum them, we have this over here. And this is also just a general form of Cauchy's integral formula, which looks like this, which allows us to find the nth derivative of our function if the nth of w equals to n factorial on 2 pi I. But just be careful, like over here, 1 is n plus 1 and 1 is n. So yeah, you can tell that this thing generalizes to the original Cauchy's integral formula if you just let n equals to 0. So yeah, maybe if you want to put this formula in exam, just to be careful, you might want to let n equals to 0 and see whether it just becomes the original version of Cauchy's integral formula. But if we're sure that it's in the correct form, all we're doing is actually just dividing by n factorial, and we take the nth derivative of f, which is similar to the previous one, 2 pi f of w, except in here 2 pi I divided by n factorial times by the nth derivative of f at w. Let's look at an example over here. Integral in the contour of modulus of z equals to 4, so not unit circle, let me just draw in black. It's a circle of radius 4, 4, 4, minus 4, minus 4. And as you can see, the singularity here is at z equals to pi, so it's going to be somewhere here, which is inside the contour, so we can apply the Cauchy's integral formula. In this case, we look very careful, right? So z minus by, so let me just write the contour using gamma. This equals to z squared on z minus by pi on 2 plus 1 dz. We want to put it in the form which allows us to use Cauchy's generalized integral formula, which actually have an n plus 1 in the denominator. So in this case, we can use the generalized integral formula to arrive at this. And of course, fz is whatever that's on the numerator, which is z squared. And yeah, 2 pi on 2 factorial times by second derivative of f at pi, which we hopefully knows how to do. And just chuck it in formula, we have 2 pi I. Okay, so this is just another question, application or interesting application of Cauchy's generalized integral formula. So I want to show that if a function is entire and it's bounded above by modulus of z to the power of k, then f is a polynomial of degree at most k. So this question might be a little difficult if we're not given any hint of what to do. Luckily, in this case, we're actually given a hint. So, which is that, well, this question is put under Cauchy's generalized integral formula. So we basically consider this thing over here. In your exam, they should give this hint to you as well. It's really difficult for them to just assume students do this. And then we can use the circle inequality and use our just below ML lemma over here. So this is just by using ML lemma. We have this thing over here. If you let r equals to infinity, so let's let r equals to infinity, we can show that this thing actually approaches 0, because well, for positive n, right, we have like k plus n plus 1 is greater than k. So the top approaches r to the power of k as we let r very large, and the bottom approaches r to the power of k plus n plus 1. So yeah, using the ML lemma, we can show the right hand side actually approaches 0. So we can show that f to the power of k plus n of w equals just well approaches 0. And then using the Taylor series, which I will cover later, we can show that f must be a polynomial of degree at most k. Yeah. So this is just additional theorem. I think this theorem is pronounced as Liouville's theorem. So it's basically saying that the only bounded function is the constant function. So if a function, and you know that its modulus approaches infinity at some point, then well, it's not constant. Or if you know that a function, for example, modulus of fz is less or equal to some arbitrary r for all z, and you know that f is entire, then f has to be a constant. So then, and f is entire. F is entire. Then we know that fz has to equal to some arbitrary constant. Let me just call it c. Yep, and so this is Morella's theorem, which is it's really just reverse Cauchy-Gaussard. So yeah, Cauchy-Gaussard also applies in other ways. So if a contour integral around any closed contour is 0, then f must be analytic in omega. So this is an example of how we can use the Liouville's theorem. So we know that f of z is less or equal to modulus of cos z. Well, we want to show that there's some function that's less or equal to r, where r is any number. Right now, it's unfortunate because cos of z, as we know, is not really a constant. But what we can do instead is that we can divide it over. F of z on cos z is bounded above by 1. So now, by Liouville's theorem, we know that fz on cos of z is a constant. So yeah, in here, so f of z on cos z equals to some arbitrary constant c. So f of z equals to c cos z. Maybe c is not the best constant to choose here since you have cos. But yeah, that's all in here. F of z equals to c of cos z by Liouville's theorem. And that's all for integration. So any questions? Yeah. Before we move on to series? Yeah, cool. Let's move on to series then. Series, residues, and applications. So luckily this topic is also very similar to what we have learned in Mathematics 1b about series. So a power series is basically a function that's in this form. We have a constant times by z minus by z0 to the power of n. Except, well, we're in complex analysis now, so we allow every variable, so namely an, z, and z0 to be complex. And the radius of convergence, stuff like the radius of convergence idea, is also carried over from Mathematics 1b. If radius of convergence is 0, then it's only convergent at z0. Yeah. And we can also integrate power series term by term. So if I have this thing over here, then f of z equals to sigma n equals to 1 infinity. And that's going to be an z minus z0 to the power of n minus 1. Just be careful about the change of like the starting point over here, because when we have n equals to 0, there's actually no z minus 0 term. So when we differentiate, it just becomes 0. So we have to start at 1. Or you can just write out this thing like a0 plus by a1 z minus z0 plus by a2 z minus z0 squared and then differentiate. That might help us to see it clearer. And similar to integrate, we can find the antiderivative by just integrate each term. So even n equals to 0, infinity, an on n plus 1, z minus z0 to the power of n plus 1. And this is a ratio test. It's not quite the same form as what you have seen in Math 1b. So just be careful, an is only numerator instead, an plus 1 is only denominator instead. But the more powerful fact about this formula is that just by calculating this limit, we can obtain the radius of convergence. So let's look at this example over here. We have a random h of z equals to just sum of n times by z plus 3 to the power of n. And we want to find the center, radius, and just expression of h and where it's analytic in. So just by definition of power series, we have everything over here. The center is going to be minus 3 because this thing equals to sum of n equals to 1, infinity, n, z minus by minus 3 to the power of n. So the center is going to be minus 3. So center is minus 3. And if we do the ratio test, we have this expression over here. Radius of convergence is going to be 1. Yep. So that's how we can find the radius of convergence and center. Center, we just look at what's in the bracket. Radius of convergence, do the ratio test. To find h as an expression for elementary function, so this is a very classic question. So they put some random n in front of the expression, or they put some n below the expression. We'll look at both examples. When n is in front of the expression, that might be a hint for us that we should integrate. So what we can do is that we can pull out z plus 3. So this form looks like some nice antiderivative. This thing can be integrated pretty nicely, right? And we can integrate this. Even though in complex analysis, when we're talking about integration, we're integration with respect to our contour. In this case, we can just find the antiderivative because every power series is analytic and every analytic function has a power series. So yeah, we can just integrate this like over here. The antiderivative of course is going to be z plus 3 to the power of n. And we have this expression over here. And we can pull the d on dz outside because power series can be differentiated term by term. And yeah, I hope we can all see that this is a geometrical series. So sum of n equals to 0, infinity z to the power of n equals to 1 on 1 minus z. This is just our below sum of GP formula. Yeah, except in here it's not z, it's z plus 3 instead. So put it in here. Yeah, we can differentiate it to make it become this expression over here. So that's hz in much cleaner form. And it's going to be analytic whenever power series converges. So as you can see here, the power series converges at center minus 3 and radius 1. So that's basically where it's going to be analytic in. This is just another example which is similar except that they have a n plus something on the denominator instead. So we want to find the center radius of this power series and just find it in terms of elementary function. In this case, it's not actually in the standard form of a power series, so that's what we probably should do first. Put it in the standard form. 2 to the power of n on n plus 1, z minus by 5 on 2 to the power of n. That's going to be the standard form of the power series, because we can't have a constant in front of z. And after converted to the standard form, we can just inspect that the center is going to be 5 on 2, and we can do the ratio test to find that the radius of convergence is half by ratio test. So I'll just write it again just in case. It's this thing over here, modulus of an or modulus of an plus 1. Yeah, we have half by doing that. When we have a n plus 1 on the denominator of a power series instead, what we might want to do is that we want to just differentiate both sides. But in this case, we couldn't do that yet because, well, differentiating it doesn't cancel out the n plus 1. So our trick is that we can multiply z minus by 5 on 2 to both sides. So we have this thing over here. And then we can differentiate both sides. The n plus 1 in here carries down and cancels out with this n plus 1 over here to become 2 to the power of n times by this thing over here. And yeah, this is our GP, which is what we know well. So yeah, that's the sum of GP. Just by doing sum of GP, we have this thing over here. And we can just, well, integrate both sides to find the antiderivative, and also just, well, rearrange to find f. And to find c, when we're doing antiderivative, we always have a constant c over here. To find c, we take note that in the original example, if you just let z equals to 5 on 2, we have f of z equals to 0. So in that case, we can just substitute in here to find c. Substitute c, and we can find that c equals to 5 on 2. And yeah, the rest is just rearrangement. And I guess, yeah, we have to have, I guess this parameterization, this branch over here occurs because log of z is undefined at zx equals to 5 on 2. I mean, sorry, this means dividing by 0 when x, wait, that should be z, sorry, that should be z, when z equals to 5 on 2. So we just redefine it to make it entire function, to make it more continuous. And the next coming up is a Taylor series. A Taylor series is basically same as a power series, except that the an equals to the nth derivative of z0 at z0 or n factorial. And yeah, definition, if z0 equals to 0, then we have a Maclaurin series. But I just like to call it Taylor series. To find Taylor series, we could differentiate every time, right? We could just like differentiate infinite times and chuck it in the integral, but that might not be the best idea. Often or not, we remember the standard power series. The most common ones are the GP. So that z to the power of n equals to 1 on 1 minus z, or the exponential function. And that's the e to the power of z equals to, oopsies, sorry. That's not the one. E to the power of z equals to n equals to 0, infinity, z to the power of n on n factorial. So those are the most common ones, but it would be nice if you also remember the trigonometric and hyperbolic trigonometric ones. So in here, we can find the power series much easier by considering the power series of e to the power of 3z. So basically, let z in this expression to become 3z. By doing that, we have what's in here. Yeah, and the rest is just simplifying. Since in Taylor series, we have to put it in what's called in this form. So it's put it in this form of a power series. We just have to factorize out. We just have to do some factorization here. But yeah, that's it for this question. Technically, we could also put the 2 inside the power series, but it's just a little iffy because we might get to the case of 0 to the power of 0. I think some publications define it as 1, but it's not agreed on, so you can choose to start at 1 over here. Taylor series are often very nice because you can differentiate it and integrate it infinite times and represent an entire function. When we do not have an entire function, we have to use something called Lorentz series, which exists as long as the function is analytic in some annular string. So if the function doesn't have to be analytic inside the ring, it just has to be analytic like here. Then it has a Lorentz series. For Lorentz series, basically in Taylor series, we always have positive powers of z. In Lorentz series, we just allow negative powers. So as you can see here, we start at z equals to minus infinity and go to infinity. So we allow negative powers. And that's all. And this thing over here, this is just a fact that I guess we can remember, but it's unlikely we will have to. So let's look at this example over here. So we want to find the Lorentz series of this thing, of this function over here, for the annulus of z minus 1 greater than 1. Let's just quickly sketch it out. The first step to do Lorentz series questions is to always sketch it out. So the f of z is analytic everywhere but z equals to 0, 1, and 2. So that's 0, 1, and 2. We want to find the Lorentz series expression for annulus z minus 1 greater than 1. So let's just say it's like here. We've centered 1. And luckily it exists because we know that the function is analytic everywhere outside z minus 1, modulus of z minus 1 is greater than 1. To find Lorentz series, often we can break it down into partial fractions, like this. Well, we can see why it's useful later. So, number one, what should I say? Okay, so 1 on z is its only singularity is at z equals to 0, right? Like here and here. So it's actually analytic, in the annulus ring we're interested in. So it actually has a Taylor series. So we know that this thing is only going to have positive power terms because it's analytic everywhere inside our interested domain, which is z minus 1 is greater than 1. And similar to others. Never mind. So I think this explanation might be a little confusing. So let's just use the GP method, sum of GP method. So yeah. After we have this partial fraction over here, we want to express each of them as powers of z minus 1. So good luck, but it might take your time to do this. As we can see over here, there will be some z1 on z minus 1 terms. This is because we have z minus 1, we have this, oopsies. So you just have to beware that we need to make power series convert. We need to make a power series, make sure that it actually converges in the first place. In our GP, if I set n equals 0 to infinity, z to the power of n equals 1 on 1 minus z. This only works if modulus of z is less than 1. That's for GP. So if you want to find 1 on z, for example, 1 on 1 minus z, where z is greater than 1, then we have to do something like this. 1 on z times by 1 on z minus 1. In this case, we have a new GP. But the nice thing is that 1 on 1 minus z, 1 on z is actually modulus is less than 1. So this thing actually converges. So yeah, I guess we don't have to worry about whether it's analytic or not, but the most important thing is to just, when we're summing GP, just to make sure it converges in the domain we're interested in. This case is z minus 1 is greater than 1. So yeah, we have three GPs over here. The only nice thing is 1 on z minus 1, which is already in the power of z minus 1. But yeah, here. Let's see another example over here. So f of z equals to 2 on z plus 2i minus by 5 on z minus 4. Again, let's quickly draw where its singularities are. The singularities are minus 2i, which is over here, and 4, which is over here. And where's the center? 2. Over here. Wait, let me just draw the center in red. Distinguish it. And we want to find a power series which converges at z equals to I. What's this radius? This radius is root 5. So it's going to be like here. This is the circle in which we want to be convergent in. To converge in this circle, wait, let me just draw another diagram. Oopsies. Wait. Okay, let me just draw it here. Wait. Okay, yeah. To converge in this circle, we can consider a power series that's analytic in this ring over here. So that's 2, that's 2, that's 4, that's minus 2i. We can consider this annular string. Okay, sorry, this is terribly drawn. So this annular string over here. So basically, once that's between, that passes the annular string in which the inner circle passes through 4 and outer circle passes through minus 2i. We can see that there's a Lorentz series here because, well, the function is analytic in this annular string. So what we're interested in is this. 2 will become, because it's the radius of the inner circle, which is here. This radius is 2 and this radius is root 8. Yeah, and then we can just try our best to find the GP. Okay, again, please take your time when doing this. Like this looks very like complex, so and just be careful to make sure the GP converges. If we have stuff like 1 on 1 minus z, we want to express as a GP. We want to express as like a power series, but we want to do it for z plus 1. Just remember to always do this. Yeah, so basically it's just a gist. That's a gist over here. I'm going to try to make a GP converge, and yeah. That's the Lorentz series. Lorentz series also there will not ask you really to simplify it, so you don't have to put it in form like sum from minus infinity to infinity. As long as we have put it in a valid form like this, it's accepted. And yeah, that's just the answer. So I'll pass it to Tom, who will do singularities and residue theorem.
Some of these might have typos because like we're editing this like an hour ago, so this is a typo. I'll just point it out. Okay, so for singularities, we have like a bunch of like classifications for some of these singularities. So I guess like here we have an isolated singularity. So basically just like it's any point which the function is analytic on, like on like some like punctured ball, but it's not differentiable at that point. I guess like the more important ones are like these three here, which is, so like the first one's like a removable singularity. So if you call like the CMs, like the coefficients that are Lorentz series, there are no like, basically no negative powers within the Lorentz series. So I just like, I can like give examples for each of these. So easiest example is this. So I think it's something like ZQ 3, yeah, so on. Point being is that when we like expand this out, we'll see something like z squared with 3q plus z for 5 factorial minus dot dot, and you'll see that like none of these terms have like a negative power. So like when we sub in like our number, like of like in this case like z is 0, like we're basically clean. So it'd be like 1 minus and like a bunch of zeros. So it's kind of like the limit is almost like basically defined basically. So that's like essentially a removable singularity. Next, you have like poles. So like the one I like to think about this is either like there's gonna be like a finite number of negative power terms. So another example I can give is something like this. So if you have like 1 on z minus 2 squared, like obviously it's a power of -2, so that's like a finite number of negative terms. Like I could also have like this if I wanted. So like I guess like that counts, or maybe something like this. Like I have 2 negative powers basically. So as long as it's finite, that's the point. Like if that's the case, then we call that a pole. We'll discuss about like the power of the pole, whatever it is. However, if that is not finite, like it's basically an infinite number of terms, then in that case it's called an essential singularity. So in examples of like this, like e to the 1 on z, how do you, what is this equal to again? It's like x to the n on n factorial, right? So yeah, so like it's like 1 on z to the n on n factorial. So like we'll see like this thing goes to like 1 on z, like I'm just seeing the factorial thingy. It's basically like 1z plus 1 on z squared plus dot. Like point is that you're gonna have an infinite number of like these negative power terms. If that's the case, then it can't be a pole because it's not finite. So therefore it's gonna be like an infinite number. So therefore we just call that essential singularity. Okay. So now we can like I guess like figure out a way to like determine each of these singularities. So for the first one, if the limit as z approaches z like 0 or like f of z, we have a removable singularity. So it's like this thing here where like we don't need to like do anything to the function. Like all we need to do is like check, does the limit exist to like the number that we care about? It's like the limit as z approaches 0. So like there's like pretty like a well-known like limit from like the sandwich room or whatever, but like you can still apply in like the complex case and it will still work. Next, to check like the poles, you need to like actually like times the function by like some like kind of like factor basically. So if you times it by specifically a high enough power k, and then the limit then at that point exists, then we'll call that a pole, specifically order. This should be same thing. Like we say k is in. So like just a random example again. Like we're just analyzing this. Like should we times this by like we can times this by z minus, obviously we came about z minus 2. Like if we do this for numbers that are too low, like 1 or 2, like this ain't gonna exist because like this will either look zone in like z minus 2 or something. If you chuck in 2, like no, it's still like you divide by 0. But the moment you times it by 3, then oh hey look, this will like go into 1 essentially, and then at that point the limit will exist. So like you want to just find the minimum number, not like we could do like 10, but like that like obviously like that's like too high basically. So I want to find the minimum number, and that minimum number is just like the order of like whatever we're dealing with. Finally, because like the infinite case from like the essential singularity, like basically what it seems like if we times it by z minus k of like whatever k value we're dealing with, like if k isn't like high enough, like basically like if you sub it infinity, still won't work. At that point, like okay, just give up. Like it's an essential singularity. All right, next. So yeah, this is the thing I was saying, like the pole of order. So like essentially, if like z minus 2 cubed, like whatever that like number was, you're timesing by like z minus 2 cubed, like that 3, it's just the pole of order 3 essentially. Additionally, like easiest way I like to think about this is like you know when you do like polynomials like x minus 2 cubed, like x plus 1, 7 or something, like I say like the x equals 2, that's like a triple root, and like the x equals minus 1, that's like a root of like power 7 or something like that. It's kind of like the same thing here, where I'm just looking at like the power basically. Obviously that's like not true for all cases. Like I'll point that out with like one example later. That's usually how I like to think of it, because like I can usually get away with it. So that's like for poles, like when you just divide like the 0 kind of thing. Oh yeah, you just got like simple poles. So like it's just order 1s, this is pretty easy. And you also got like the 0 of order, that kind of stuff, which is like literally the same thing as this. Like if I have like z plus 1 to the 10 or something, yeah, this is like this is a 0 of order. Sorry, like z equals minus 1. That's a 0 of order like 10. So it's like pretty obvious. And then yeah, simple 0 is pretty easy again. Okay, so classify these singularities. So we basically just want to find, okay, like what will make this thing go 0? So, or at least like in the denominator, I mean. So like I mean for the bottom, we just factorize it. Z plus I pi, Z minus I pi. Okay, so like informally, like how I can see is like, oh, actually no, wait, no. Obviously we see like the poles are just like plus or minus I pi, but then to actually like classify these singularities informally, I'm just gonna say, oh hey, look, like this power here, that's just like a power of 1, and like this thing here is also a power of 1. So if that's the case, then like both of these are simple poles. But you know, like obviously in the exam, like let's actually do this properly. So remember like the singularity definitions. Like this limit ain't gonna exist. Like obviously like this one go to 0. So we need like maybe like resort to number 2. So times it by like z plus or minus like the I pi to like some power. And I'm just claiming that like just doing a power of 1 is enough. So let's times this by, okay, let's just do like z plus I pi first. So z plus I pi times z ez. Okay, yeah. Forgot to say the lim from the before one. But yeah, obviously like these lines were like, oh yeah, you guys can see, okay, good. Yeah, but you can see how like these would just cancel, so like we're just left with this, and yeah, something in negative I pi, we won't like break the denominator or anything. So we just sub that in, negative I pi, or negative 2 I pi. This would be like a half. Okay, so yeah, AC I pi is like minus 1, so like negative that should be fine. Yeah, so that thing would be minus half. It's similar for the other one, so oh yeah, wait, I just like redo this point again. So like yeah, we just like times it by like we're here, like if we sub in minus I pi, limit doesn't exist. The moment we times it in and then try to do the limit, yeah, the limit exists. So power of like 1 is enough. So it is a simple pole. So I'm gonna speed run the other part. Okay, I'll just do it here. Yeah, okay. These are z plus I pi, yeah, okay, and I'm subbing in here, so like I pi, et I pi, 2 I pi, this thing is a half et I pi, et I pi, it's negative 1, so minus half. Let's check that's true. Yeah, so like all of these, both of these are like simple poles. Okay. Okay, great. The only problem now is like I'm kind of out of space. So next one, classify these singularities. So once again, we're just like, what makes this like denominator go to 0? So like obviously just like looking at this, treat like a polynomial or whatever. Z equals 0, Z equals 4, Z equals 2. But then like the hard part now is like actually like justifying, okay, like what's like the pole order basically. So basically what I'm claiming is this like too small? Is this like fine? Okay. Yeah, okay, hopefully it's good. So just for the first, I should try it smaller. So for when dealing with z equals 0, once again, I'm kind of just claiming, obviously can't be a, probably not a removable singularity, if you sub in, you divide by 0. Let's consider just times it by z. So like I'm just like too sick to like write it. I'll just say this. Lim z approaches 0, like times this by z, so like z minus 4 cubed, so just cancel. Okay, and then just sub in like 0, so it's like e2 minus 0, minus 1, minus 4 cubed, minus 2. Well, I'm just going to give me a calculator. Alright. Okay, the top we can't really do anything. Bottom. 128. Okay, so like obviously this like, I mean it doesn't really matter if it's 0 anyway. Like point is like it goes to an actual number. So like how it works, yeah, okay, it's the same. So next, z equals 2. So this is like, this is a big one because you might think like, oh okay, like I did say like just look at the power and like, oh okay, like z power 1. So probably a simple pole. Problem being is that if we actually sub in z equals 2 to not just the bottom, but also to the top, we see that we have e to the z minus 2, so like, what, e to the 0, so like 1, and minus 1. So you have like 0 and 0. So that's like, that's probably like sus, so like we need like, do more work basically. So you recall from, I believe 1a, like if you're trying to find like a limit as z approaches like some number, and it goes 0 and 0, we're gonna use like L'Hopital's rule basically. So, like, I never knew that like they had to be analytic to apply L'Hopital's, not gonna lie. But who cares? We're just gonna do it anyway. So, diff the top and bottom basically, and then try apply the limit then. So if we're diffing the top, that's like e to minus z2. The minus 1 goes away. Okay, so this is annoying. We have like a freaking triple what's that? Triple like product rule kind of thing. So like diff each one of these separately. So like z minus 4 cubed, z minus 2. Okay, so like 3z and then z minus 4 squared, z minus 2 plus, okay, diff the other one, that's like z minus 4 cubed. Okay, once again, like the freaking limit, z approaches 0. Sub in z equals 0 for like this entire thing. So like, this is column, the bottom, okay. Alright, this is not too bad, okay. Because when we sub in z equals 0 for like here and here, doesn't matter what these are, they're gonna be 0 anyway. So let's just sub into this. Wait, this is, oh, okay. Wait, I lied, no, z equals 2, not z equals 0. But even then, I know 2 of these factors are gonna have like the z2 bit, which is like this and this. So those will go away anyway. I only need to do with this, because it doesn't have the z minus 2. So 2 minus 2 cubed. Screw the calculator, I don't need it. Okay, it's 16, I believe. Oh. Wait, I can't freaking math. Because I forgot it was 0. Yeah, okay, e to the 0, so 1. Okay, the bottom is like just minus 16 basically. Yeah, okay, so that lines up. Okay, finally, yeah, so like basically my point in this one is we didn't times this by z minus 2 essentially. So the limit was already defined, like without even like touching the function basically. We're like, yeah, we did like the diffing thing to the L'Hopital's, but the limit does exist. So what that means is like, oh, okay, go back to the very start. Limit exists for like just that function purely, so it's a removable singularity. Okay, z equals 4. Okay, this one should be calm as well because we're just timesing, like if we do it at the bottom, it's 0. If we do it to the top, it's not 0. So like no like kind of like L'Hopital trick again. Once again, I'm just claiming times the f of z by z minus 4 cubed. So we just have the expression of z minus 2 minus 1, z, the cubed part goes away. So again, the limit as z approaches 4 of this. Okay, so like this is pretty easy. E squared minus 1, 4 minus 2, e squared minus 1 over 8. Yeah, okay, cool. So yeah, this one's like a third order pole because we times it by z minus 2 cubed. So then that, by doing that, we make the limit exist. Alright, easy. Okay, so next, so like, where's like the coolest part of this course, which is like just the residues, or at least like the CE part of this course. So suppose like f is holomorphic on like, they're basically just like make sure like nothing goes wrong basically. And you have a bunch of like Lorentz series. So like the C of n just represents the coefficients of like your Lorentz series. So one way to define the residue is it's just the coefficient of your power of like the power of like minus 1. So if I'm just gonna make it up, like 1 on z, okay, dot whatever, plus I don't know why I did that. Okay, yeah, whatever. So like here you have like a bunch of like coefficients or whatever. Now, what I'm claiming is that, like, okay, just look at the coefficient with the power of -1. So obviously that's this one. So, like, the coefficient here is 2. So, like, oh, okay, that we're just going to define that as the residue. So, like, that's one way to see it. Why is this? Oh, okay. So, like, that's like the easiest way to, like, it will depend on question by question. The other way to define the residue is like this, like, scary looking formula, which is like, if you have like a pole of order n, so it's like basically just this essentially. So like if n is like 1, like the diffing part doesn't really count. But like if n is like 10, like you're gonna have to diff this like 10 times, which is like kind of crazy. Okay. So from this, okay, I don't know why it's a pretty example. Who cares? So it has singularities like k pi, obviously, because like that's what's gonna make that thing 0. Yeah, calculate these residues. Oh, sorry, calculate these singularities. So, residues of these singularities. So, like, I guess like what we can do first is consider a bunch of cases for k. So, let's say k is 1. So, obviously, like, that just means z equals pi. So, like, essentially, what does that mean? Let's see. Oh, okay, yeah. So like essentially what that's saying is like the limit as z approaches 0, oh no, z approaches pi, sorry, of our g of z. So like once again, no need to like do like the fancy stuff of the what do you call it? The times it by like z minus to like some like specific power k. I think z minus pi squared. Limit as z approaches 0. Oh wait. Oh wait, this I can easily fix this. Okay, so what I can do is like z minus pi squared, like no problem. What I'm going to do here though is I'm going to say sine squared of pi minus z. So like it's just a known fact like sine x equals sine pi minus x. I don't know, that was like proven like year 10 or something, I don't know. Point is that like, if I have z approaches pi, like I can basically just like do some like manipulation of the algebra. Basically what like reduce down to is like z approaches 0 of z squared over sine squared z. And then obviously that thing will go to 1, okay? But then obviously, like, oh, okay, it's like some like BS like algebra stuff. Wait, how's it removable? I thought this thing would go to 0. Let me think about this for seconds. Oh wait, I'm okay. Wait, I'm kind of tripping. I guess like one way to see is like you could just probably I don't know if I like messed up like the algebra here, but just like sub in z equals like 0.0001. Like wait, like pi minus like 0.001 or something. Like the limit will exist. Like I'm just like too cooked to like see this. Point is like if we know it's a removable singularity, remember that it has for the removable singularity there are no negative integers. Negative integer powers. If that's the case, well, for the residue, for like that one definition, we're asking for that -1 coefficient. But because it has no negative coefficients, well, guess what? Like the residue is 0. Okay, so that's how we can get this. Next, for z equals 0, it's a simple pole. So, alright, this one. Okay, this is the part where I was actually meant to do the trick, which is times it by z. Okay, so it's not. Wait, it's not. Or oh no, deal with that later. So times it by z. So like z times by g of z, that becomes z squared. Z minus pi squared sine squared z. Also, I forgot to clarify. This is like when k is 0. So like obviously like z will go 0. Okay. So yeah, this is the part like where I actually do my trick. So z approaches 0. Sorry, z sine squared z. Yeah. Okay. So like, just do the limit to like each of these expressions, like this one and this one. The first one, that will approach 1, like cool. Next one, like minus pi squared, pi squared. Okay, good. Okay, so like we're kind of like dealt with like the simple cases. So what happens if it's like neither of them? So like when k is not equal to 0 or 1, we claim that this is a pole of order 2. So this might not seem obvious because like, okay, like this sine squared, like I can't just, okay, yeah, like basically how I'm going to say this informally is, wait, is it a joke that like sine z is equal to z? Because I'm basically just going to use that. Like essentially, like if you just think it's like that, then like it's basically this thing is approaching z squared. So you can basically look like, oh hey, the power is like 2. So informally, that's how you can think about it. But if you actually want to like prove this like previously, or let's take the residue of it. Remember, you have to like do this like really like remember like that formula here. When n is like greater than 1, you have to diff it. So like in some cases you can, some cases you like I mean you can, but like it's just like not worth it. It just happens in this case, like if you times like z minus k pi of here, or like squared of it, like you have to do like a really bad like quotient, like a bunch of product rules. So like I mean like sure if you like have time in the exam, but we're gonna do some like we're gonna try like find some other method, which is the like try to find the coefficient of like that -1 power essentially. So the strat is to try and find the Taylor series of like at least like sine squared around k pi. So I already claimed that this thing is sine squared z k pi minus z. Okay, like you can do this like what I said before here, like the pi minus x. You can say sine of x minus pi, but then like that would introduce like a negative. But this thing is like squared, so like this should be fine. Next, k equals 0. Wait, should I use? Okay, wait, I can't really use k. It's bad. Okay, just I equals 0 and then infinity. Okay, wait, I have to like use this. I need 1 I. So then it was like the factorial stuff. So like 2i plus 1 factorial. Z minus k pi, and then like this thing's to the power of I. But then that's just sine of z minus k pi. So like obviously we're gonna like power that to like 2 because this is sine squared. Okay, what was the next? Okay, so yeah, unfortunately this is just like super bad, like super janky. Z minus k pi. Where is it? Okay, so we have to like reciprocate that entire thing. So it's like we're gonna do like a couple terms. So it's like z minus k pi minus z minus k pi cubed 3 factorial plus z minus k pi 5 minus lambda, and obviously like that entire thing is squared. So I guess like what you can do next is maybe like notice like all these have like a z minus k pi, so like factorize that out, but like this is under the square, so we're really factorizing like a z minus k pi out of the squared. 1 minus and then like this stuff. Squared. What did I miss? Oh, right, yeah. I took a power 1 of each of these, not 2. Okay, is that it? Okay. So, like, that's like a massive sum there. But why does this help? So, whoa. Okay. Okay. Because we, like, remember, like, God damn it, okay. What's going on? Yo, Brandon, we have technical issues. Bro, I got locked out. The freaking... No, it's just like the freaking... The notebook is like cooked for some reason. Oh yeah, it's read only. Like,
Oh,
what?
bear with us.
Yeah. Take like a 5-minute break. I don't know. Are you sure? Should we save it?
Why should we
Wait, save a copy. What would I do? What if I check a live stream to see what I did? I'm gonna do that. Wait, figure out something. Okay. What? But I literally didn't do anything. It literally just like froze. Did it? Maybe load a new notebook.
No, but like, it's not.
It's not an issue if the notebook is.
Maybe. Locations no longer available. What?
Yeah, just a minute. Wait. Okay. What a clutch. What a clutch. Okay, this is the. Oh, thank you, man. I needed that. Okay, sorry about that delay. Okay, what the hell was I saying? Okay, yeah. So the idea is that like this, like that one, like this sine squared z. Wait, Brennan, how are you able to like make this like tab like just stay here? Is that possible?
What do you mean stay?
Like, cause like every time I draw, like, it just goes away.
What goes away?
Wait, if there's like a rubber thingy, then
There's a rubber band. Yeah.
wait.
If you press like the top button. Sorry, bottom.
Oh, okay.
Like this one.
Oh wait, I should just been using that. Okay.
Are you good now, boss?
Yeah. Okay. Because I don't need it. Like, yeah. Oh, easy. Alright, thanks, man. Okay. For the third time, I'm gonna say this. Yeah, like this. 1 minus sine c squared. Like we already found like the expressions like that. Now what I'm going to do is like, yes, we have like this like really convoluting. Oh. Sorry, I forgot to say one thing, and it's that. Wait, is that squared? Okay. Like technically, I can. This is so annoying, but what I can like technically do is take like just get this out of here, like this squared, and then put the square on like the whole thing. So like I have like 1 minus. I'm gonna unnecessarily do that. Minus z minus k pi 4 factorial plus dot dot or whatever. Now 1 and like put the square under like that whole thing, and then just see that the like remember like the 1 minus x that's equal to like 1 plus x plus dot dot dot, like x squared and so on. We see like that's like literally like the same form here, except like the x is like so ridiculous. Like this x is like this entire thing. So what we have is like the sigma I equals 0 infinity of like literally that entire thing. So like z minus pi squared plus dot dot. That thing's take to the power of I, or like, can I say, surely I can say 2i. No, I reckon it's 2i. Yeah, because like this part here is like this, but then there's the 2 on the outside, so sure I can do that. Yeah. Okay. Then what I claim is we just focus on like the z, and then like this tiny thing, like the z minus pi like squared, and we just divide that z minus pi squared. And we yoke out this part. Like obviously, if we like combine like this entire thing, that's the 1 on sine squared z, and we combine that with like the numerator of like the g of z. Basically, we have this I equals 0 infinity. How many 2 c's? Okay, just like this entire thing. And what I claim is like, remember, like this is still g of z, albeit it's like just very complicated. If we can force out the coefficient of like the power with the -1, we basically got the residue essentially. So, the strategy here is to express this part in terms of z minus k pi. So, it might like seem like kind of daunting, but like we can do something like this. So, force out the z minus k, like just for z, get out z minus k pi, but then like plus k pi to like counter that kind of. And then what the other one? Like z minus k pi plus k pi minus pi. So something like that, and then z minus k pi squared. So okay, this looks really bad, but there can be something done here. So this is like z minus k pi plus k pi. And then here, like, okay, we're like square, it's like the a plus b squared. So z minus k pi squared plus 2 of z minus k pi minus pi plus k pi squared z minus k pi squared. So like also like you might be like wondering like, okay, like what about the other like terms, like specifically like this like massive sum, doesn't that like contribute to the like could that like contribute to like the -1 power? My claim is no, because like the only like real I value that's going to be even remotely useful is when I equals 0, because when I is 0, yeah sure, this thing's 1, but let's say like let's consider what happens when like I equals 1. In that case, like the lowest power here is like 4. But then when we times it like across here, like across like this entire mess, like the power is going to be like I believe, okay, so you have like with 3, 2, so it's 1. Like the minimum power if you like times across here is going to be like something like 4 or 5, like 4 or 5 basically. So like if there were negative terms here, then yeah, they could definitely contribute to like the -1 like coefficient of the residue. But because like these numbers like way too high, we're not gonna like get any like coefficients in there. So like I said, the only like part that's gonna be useful is when I is 0. So like this thing just like power of 1. So like essentially we just like put our eggs in this basket and just like focus on this. So where are we gonna get coefficients of? We're gonna get coefficients of z minus k pi to the power of like -1. So that's we have to like expand this out. So like there's only like 6 things to deal with. So like this times that. Okay, like if we have z minus, okay, it's like this times this. That's like power of 3 divided by 2. So like it's like a power of 1. So like no is too high. Z minus k pi here. So like there's a power of 2, and then just divide the power of 2 again. It's like a power of like 0. So again, not really useful. Now this one, it looks like it's a power of 3, but remember, this is just a constant. So we have z minus k pi, so let's say some random constant, divided by z minus k pi. So that then becomes 1 on z minus k pi, which is exactly what we want, the power of -1. So again, just look at the coefficient of that, which is just k pi minus pi squared. Okay, so like that part here is going to contribute to like our residue basically. So next move on, k pi times this. Okay, so this is like a constant, like who cares? Z minus k pi divide this. So that's a power of minus. So that's a power of -1. So there's like already that's like a pretty good start. So just look at the coefficient of this. So like cover this and cover that. So we have like 2k pi minus pi, and then times that by k pi. Okay. Finally, this is z minus k pi times y, again like a constant, and like what, like another constant here. So it's not a power of -1, it's a power of like a -2. So again, like we're not really after that, so like who cares? So this here is like by like essentially selectively yorking out the coefficients of the power of -1. That's how we can get like the residue like number basically. So okay, like essentially this, but like I'm like 2c to like expand this out, so it goes dot dot dot. Okay. Okay, I'm really taking up all this space. So next is like Cauchy's residue theorem. So this is like quite useful whenever you're like trying to do like it's essentially an extension to like Cauchy-Gaussard theorem. Like when you essentially deal with like singularities in science. So like if it's 0, then like if you have no singularities, 0. If you have singularities, well, like that's the point of this. So the integral is equal to 2 pi I times like the sum of all your residues within like that like contour basically. So here have this example. Consider this function. Blah blah. Find all the singularities. Like classify these. So we have f of z equals z 2z plus 5z squared plus 2. So find all the singularities. Again, just make the denominator 0. So factorize this. So like 2z squared plus 1. Z squared plus 2. Okay. And then we just factorize this. So like root 2z plus I. Easy. So then here, all of these are, sorry, I'll say the roots first. Root 2i plus or minus, I missed out, 1 over root 2i. So those are all our singularities, and then like obviously all of these like symbol poles, because like once again you can't just like look at the power of like each of these, or like power of 1 basically. What was the method there? They just, yeah, okay, they didn't even like say it, they just said it. Okay, next, what was the question? Find all the residues there. Yeah, okay. So I want to find all the residues that lie inside the unit circle of like these singularity. So obviously like root 2i, like the plus or minus whatever, they lie outside of the unit circle, so we're not really going to care about it. We're only going to like consider like these ones essentially. So remember like how to find like the residue. So this time we're not going to consider like the coefficient like the -1 basically. Just do the like that complicated looking formula, which is like this. But it's a power of 1, so like it's like calm. Like we don't need like do any diffing. So we just need to do z. Okay, let's just do minus. Okay, wait. Okay, limit z approaches 1 on root 2i of this essentially of f of z. Yeah, I said f of z. Okay. We're not gonna really touch the z squared plus 2. That's like fine. But like maybe split this up. Root 2z plus I, root 2z minus I. I can just times this by root. Oh, okay, yeah, exactly. Yeah, okay. So I definitely remember this bit like when like learning this part of the course. So a common mistake a lot of people do is like you know, like, oh yeah, like it's pretty easy like find the root, but then they just go ahead and like cancel this. Because the like kind of rule is that you need to times z minus like whatever your complex number is. Because like when they're factorizing this, like usually they leave a like not monic basically. So you need to ensure that you have to first like take this root 2 out. So like root 2 and then like doing something like that. That way then you can like cleanly take this out. But you see how like this root 2, because like it's usually a common mistake for people to just like forget about that. Once you deal with that though, then it's like pretty easy. So like z root 2 z squared plus 2 root 2 z plus I. At this point, like, because like limit as like basically here, limit approaches like that for this expression. At this point, just calculator. So like 1 over root 2 I answer root 2 answer squared plus 2 root 2 answer plus I 0.16 or just 1/6. Okay. Similarly, do this for the other ones. I'm just going to go on the side now. Limit z approaches minus 1 over root 2 I of, once again, like, who's trust that, like, it's basically this. Z equals 2 root 2 z root 2 z minus I. Like, I'm pretty sure like this thing also goes to 1 and 6 as well. So like that should be relatively calm. Those are all your residues. Okay. So now like the part C. Yeah, hence find this. Okay, okay. So like find this somehow. Let's start from like basically like by considering the like this one, like the z 2z to the 4 plus 5z squared plus 2z basically. What we're gonna do is so this is like under the unit circle, that is. So what we're gonna do is let z equal to ETI theta. So like pretty sure like z equals IEI theta. So like bunch of diffing style. Let's see what happens. So IE theta from the DZ 2z y theta plus 5 E2I theta. See what happens. Like didn't really do much like simplification. What we're going to do here is then try and because the whole point is like we're trying to go. Oh, sorry, I forgot to say bounds. Obviously, like you know when you do like 0 to 2 pi, you do like a 360. So those are your bounds. But then from here, like remember like the whole goal is that we're trying to get to like the cos squared theta. So I guess like an intuition is recall like cos theta. That's equal to like e to the I theta plus e to the minus I theta all over 2. So you want to try to see that expression like pop up somewhere, or at least like when you're squaring it, it's like e to 2 I theta, like somewhere along the lines of that essentially. So we better try to see that somewhere here. And I guess like a motivation here, divide the whole top and bottom by e to 2 I theta. So we're going to see it's like e to 2 I theta plus 5 plus 2e minus 2i theta. So maybe like rewriting this, we have 5 plus 2, factorize that out. Okay, so like what do we do from here? Maybe like we could do like some little like side work, which is that, remember like cos theta equals e to I theta plus e to the minus I theta 2. If we square the whole thing, that's like 4 e to 2 I theta plus 2 plus e to minus 2 I theta. So that's something like that. So it's quite close to this expression here, except we just have like missing a few things. We're missing the 4 and we're missing the 2. So like just like one by one, let's get the 4 in there. So like e to 2 I theta. Okay, okay, whatever. Yeah. So like I'm gonna force a divide by 4 expression. Obviously, like that's changing expression. How do I counter that? Let's times this thing by 4. So like that thing will turn into 8. Because sure enough, like when I do like 8 divided by 4, that thing will still be 2. So it's still like valid. Final thing I want to do is get that plus 2 in there somehow. So 2i and then plus 2. Oh, yeah, so we have this. So we have a plus 2, but again, it's like I'm kind of like changing expression. So I need like, since I plus something, I need like minus something to like basically counter that. So like, how much am I actually adding this by? So like 2 times 8, that's 16. So divide by 4. So I'm basically just plussing 4 to the denominator. So to counter that, that's minus 4. Whoa. Okay. So then this thing will go into 1 plus 8, and then e to 2 I theta, this stuff. Okay, that looks like really bad. But you see that, like what we said before, that thing is cos squared theta. So let's just replace that entire thing with 1 plus 8 cos squared theta. So we've successfully transformed our like complex integral into like this like real integral basically. I should have done this at the start. Like, it doesn't matter because like where is it? Like this integral here, evaluate into two ways. First way, yeah, I just did it. Like, just doing the transform to like the real integral. Now you could actually like, I reckon you can like solve this. You know, with like if you times like the top and bottom like sec squared. So it'd be like 10 over something. But then like you can like mess with like the bounds like 2 pi just from what I can see. So you have to like do like times like 4 to like from 0 to pi 2. Like, but that's not the main point. The other main way to solve like that complex integral was again like the Cauchy's residue theorem. So let me just go back here. Remember this thing is equal to 2 pi I of all the residues. What are the residues though? We already calculated from the part B. So which was the 1 and 6 and 1 and 6. Why? Okay. 1 and 6 plus 1 and 6. Okay, wait. I know I messed something up somewhere here. Oh yeah, okay. Like throughout all these, I forgot this I thing here. So like I. So like I guess I lied. It's not integral, like a real integral. Like okay, fine. Like this part is like the real integral. It just has an I. Like who cares? So like how do you simplify this? This thing is 2 pi on 3. Okay. So like this is like pretty like we see like the power of Cauchy's residue theorem just by like finding the residues. Like really easy. It's like 2 pi on 3. But then like what does this mean? We know that like this expression here that's equal to 2 pi on 3. Like it's the same expression. Like I just said it in like 2 different ways. So what does that mean? I can then say like just get rid of the i's basically. So d theta 1 plus 8 cos squared theta. That thing is 2 pi on 3. So that's like I guess like the power of using CRT basically to solve real integrals basically. All right. Okay, we're not on there yet. Next, negative pi. Negative pi cos 2 theta. Phi plus cos. I believe that's what it was. Easy. Okay, so once again, like use the complex analysis methods, whatever, to like find this. So like this time we're not really given like the actual expression like unlike before. They kind of like gave it to us to help us. So we're gonna go the other way. So rather from complex to real, we're gonna go from real to complex. So once again, like let like the z equals like the ETI theta, that kind of stuff. This time have to be kind of careful here. So like just like over like the unit circle obviously. Now cos 2 theta, it's like e to 2i theta plus that over 2 phi plus 4. I'm going to simplify that. So like 4 and then like divided by 2, so it's like just the 2 ETI theta plus e to minus I theta. Okay. But then like the d theta, how do I deal with that? That's like, okay, like dz equals I ETI theta on d theta. So like I can like say dz, because like ETI theta that is z, like iz equals d theta. So I might have to be, okay, just ensure that, like dz over iz. Yeah, okay, this is convincing. So gamma, and like just replace all of these. Z minus 2 to, okay, let's put it down here. Z 5 plus, oh yeah, okay. Z plus Z minus 1. Okay, let's just check this all. Okay, wait, I can do a bit more work. 1 on 2i gamma z2 plus z minus 2. I'm not going to touch this, I'm not going to expand that. So 5 plus 2z plus 2z minus 1. Then what I reckon I can do is to get rid of like the annoying like the minus 2, this times the top and bottom by z squared. So 1 2i gamma z to the 4 plus 1 z 5 z squared, I believe. Okay, wait, I'm just gonna just put this here. So like z cubed first, 5z squared plus 2z. factorize the z squared out of there. 2z plus 5z plus 2. Yeah, okay, I'm seeing the version. Okay. Z4 plus 1. I guess like we have factorized the bottom, so. Let's stack this. Oh, sorry, this is squared. 2z plus 1, z plus 2. Okay, this is right. 2, 4, 3. Ooh, okay, wait. 4 plus 1 is 5. Okay, yeah, cool. Cool. Okay, so. Okay. Now from here, what do we do? Again, let's use Cauchy's residue theorem. Obviously, to do that, we need to find the residues. So, specifically, we don't care about the singularities within the unit circle. So, like, we have the singularities as z equals 0, minus a half, and minus 2. Okay? We're only going to care about, though, at z equals 0 and minus half, because that's the one only that line in the unit circle. So, we need to find, like, the residues at these points. So, and like, we also got to consider like the poles and their order as well. So this is the first time we have to like, okay, when z equals 0, it's like m, I said like m to represent the pole, m was equal to 2. So what we need to do is we have to do the limit as z approaches 0 of the diff of z squared times by like that, okay, I can't really see z, okay, like z4, z squared, 2z plus 1, z plus 2. Like this whole thing. So first times like the, get rid of like that pole, diff it, and then sub it in. So limit as z approaches 0 of, okay, like, I'm doing a diff right away. So like z to 4, and like that thing was, okay, the same thing there. So 2z squared plus 5z plus 2. Okay. Like, it might look bad, but like, oh wait. So just gonna make sure like it's actually the right expression. What? Yeah, okay, yeah. Okay, what is it anyway? I think it was. Alright, so like, it might look bad, but like, trust like, it's not that deep. So it's like 4z cubed, and then like, that whole expression, I'm just going to see that because like, you see why. And then plus z4 plus 1, and then like, the diff with this, like 4z plus 5. Oh, no, it's not plus, minus, because this is quotient rule. Okay, fine, I'll just sum in. Okay, so then at this point, with the diff, now we can sub in the limit. So you see how like, when you sub in z equals 0 here, like this one goes 0. So like, it doesn't matter what the hell this is. So 0 minus, now we can like sub in 0 here, so it's like 1. This is not meant to be anything. Okay, so like 0, 5. Okay, and then like blah blah 0, 0, and then 2. Okay. So minus 5 on 4. That's one of, that's the residue at z equals 0 for the pole order 2. It's like the harder of the two, but the other one should be like relatively easy. So once again, the, okay, like, yeah, like we don't really care about the one minus yet. Times the by minus, yeah, okay. Of, so remember, like it's this, oh sorry. So remember, we're timesing by z plus a half. So like, sure we can cancel this out, but then like, just remember like this 2, like get that out of there first. So like z to the 4, and then take out this 2, and then like, then we should be like pretty easy from here. 2z squared, z plus 2 equals, like if we sub it in, like it's not gonna like make like a 0 and 0 or anything like that. So let's just sub it in. Okay, answer 4. Easy. 17 on 12. So essentially, we found all the residues. So now we can basically just combine this. So remember, it's like 1 on 2i, like whatever, like 2 pi I, and like then at that point all the residues. So 17 on 12 plus like the minus 5 on 4, like so just minus 5 on 4. Okay, so like we see like the the two i's will cancel. This part though, like, I don't know, so what the okay, hopefully the cops aren't on their way or something. If security comes, like, you guys will know why. Alright. Yeah, okay, thank God, thank God. Wait, why did I just, okay, wait, like, whatever. Like, this will just be with part 6. Yeah, so, like, you just have the 6 there. What the hell? Spacing is insane. Wait. Okay, next, there's like a final one for me. Jeez. Use complex analysis methods to find this. Okay, like just each of those. Let me go up here maybe. Okay, so you want to find cos 2x. Like, I'm just going to use like some very informal notation here. X squared plus 4x plus 5. Yeah, okay, so like, just like, you know what I mean, like just like each of those. So what we're going to do is we're going to consider the integral from, well, can't we see gamma yet? Consider the integral of z squared plus 4z plus 5 of e to the I to z. Okay, so the reason being for this is, remember like the Cauchy, well, it's not Cauchy, like the Euler identity, like for like cosine plus I sine. So like basically what that means is like whatever answer we get out here, like we just equate the real parts, like the imaginary parts of like whatever our answer is. So that's like the reasoning behind that. Okay, but then like, what do we do from here? So we're gonna consider the like the complex integral of this expression on like some like curve. Now this is like the tricky bit, is like defining the actual like what is like the actual contour we're integrating on. So what I claim is like visually, like on like the arc diagram, whatever. So it's gonna look like this. So from a, obviously you see it's like a semicircle basically, but we're going from minus r to r, and then we're kind of just like integrating around that. So like obviously it's like a semicircle radius r. So how we're splitting that up is we're gonna get from like this part here, like minus r to r. So obviously like that's just like the real case like that we're actually just dealing with. Z squared 4z plus 5z plus, and then this contour. So like obviously like this kind of like semicircular arc essentially. So what one's gonna say? Okay, let me just like say like C like CR, I don't know, like for just for the curve. So e to 2iz. Yep. So how does this help us? This part, so the whole idea is that we want to let r go to infinity. If that's the case, well then like this expression will go to like, okay, essentially this, like I'll be like the complex stuff. So if we let r go to infinity, we want this expression. So like just don't touch this yet. We'll deal with it later. For now, like try to do this one, because obviously, like I said before, like we can do this in like two ways. Either like do this like individually, I guess, or like do this with like the CRT, like the find the residues. We'll deal with the residues later, because like do like the hardest one first, which is like resolving this. Okay, so how do we deal with this part, like the this semicircular arc? Like how does that like approach anything? Okay, okay, so the idea here is that we're gonna try use the ML lemma here somewhere. So first, let's try to make maybe okay, do I really want to? Okay, let's go back to the very start. Where's the ML lemma? Yeah, okay, so like let me just like rewrite this again. So like the integral, like whatever, like at least like the maximal value of it, it's bounded by a maximum value of our like function basically, and then just times by the length of our curve. So we're gonna remember that. Easy. So what's the maximal like kind of like value for this? We're going to consider this expression, z squared plus 4z plus 5. Actually, wait, no, we can do this easy. E to I z. Like, what's the maximal value of this? So remember that like x equals, z equals x plus yi. So like e to the 2 of I of x plus yi. So e to the minus 2y plus 2xy. This thing will be equal to e to the minus 2y. So like the exponential, like we're only taking like this part because like the e to 2xy, like just the modulus of that is like 1, so like, it doesn't really matter. So we have this. Now I guess like we can say that like if we're letting the complex number go off to infinity anyway, like the y will go to like y will basically go off to y will basically like shoot off to infinity. So in this case, this will like approach 0. Like I guess like to be more specific, we just care about if this thing is like greater than 1. That's what we care about. This part though, the z squared plus 4z plus 5. Remember, like we're like taking the absolute value of this. Let's apply circle inequality twice. So z squared plus 4z minus and like a minus 5. So then this thing is like z squared plus 4z minus 5, I believe. So I kind of like similar to what Jerry said. You might like be concerned about like the how do we remove this like inequality thing. We're letting z go off into infinity, so this thing like will blow up. So like it's pretty safe to assume like, oh yeah, this thing like would. Like we're safe to like remove the absolute value of there. Do it again. So z squared minus 4z minus 5. Okay, technically like minus and like the minus there. So it's like this, I guess. And then once again, like the higher power of the z will like dominate over like the power of just 1. So that will be safe to assume like, okay, like z squared minus 4z. I'm just taking the absolute value and all that out. But then remember that this is on the circle, so like this. At any one, like z is like any arbitrary point on this semicircle. The distance from like the modulus actually is just r, because like remember this is like the radius of the circle essentially. So we're saying like we're actually just saying r squared minus 4r minus 5. But then obviously the like technically like the absolute value of the z is the r, but like I kind of forgot to say that. Like so we just say this. Okay, so essentially what we proved is like, what is it, like this expression that is greater than this. So I can just say again, like z squared plus 4z plus 5 it's greater than this. So if we take the reciprocal, we'll just flip the sign, so we have this. And then obviously we have like that e to the, like the 2, what is it? 2iz, sorry. Okay, that thing is bounded by, it's actually 1. Because like when we take that, actually, nah, close enough. Okay, basically, please move. This thing is 1. Okay. So the maximum value is bounded by that. Now for that's just for the m part or like the MR lemma. We want to also like consider the length. So like length is like pretty obvious. Like length of this semicircle is like the radius is r. Length is, circumference is 2 pi r. So just semicircle would just be like I believe pi r. So the ML is equal to pi r over r squared and like that stuff. Okay, so what we have is like the absolute value of like that entire like integral expression is less than pi r over r squared minus 4i minus 5. Okay, And the idea, like I said before, let r approach infinity. So limit as r approaches infinity, what we'll see is like that kind of like circular expression, that will, so like, it's kind of intuitive to see, I reckon. This thing has a higher power, so like the bottom will denominate, so that thing will approach infinity, therefore the whole expression will go to 0. So this thing will like go to 0. What that means is like, as r goes to infinity, like that circular contour, it goes to 0, or at least the integral of it. So like back to like the sum of those two expressions, wherever they are. I was like, find Wally. Yeah, okay. Yeah, this thing is 0, okay? So we took like this thing as r goes to infinity. So what we really have is minus infinity to infinity of e to the 2i z squared plus 4z plus 5 dz is equal to, and that's the thing, we don't have an expression, like we don't have a number for it, but then remember, like this is one way to solve it. The other way to actually solve this, again, like the CRT, so Cauchy residue formula. So find all the residues of this expression. So e to 2iz, maybe you can like, find the singularities first, and then find the residue of those singularities, So z squared plus 1. Again, like what the hell makes the denominator 0? Minus 1, so like, so like z equals minus 2 plus or minus I. Okay, so find all the residue of these singularities, but then remember, here's the thing. So we already said like our contour basically looks like that. That looks really ugly. Minus 2 plus I, that is, well, something like here or something. Obviously this could go infinity, but the other singularity is down here. Now, thing is, we don't really care about this singularity because like it's not in our contour. We only care about this one. So we only need to find the singularity at minus 2 plus I. So how do we do that? Well, we can, I have to like z plus 2 plus I, z plus 2 minus I, and then like times this by z plus 2 minus I believe. So then what we have is this. So then like it won't like make the denominator like go 0 or something. Yeah, okay. Limit z approaches minus 2 plus I. Yeah, okay. Now just sub everything in. So 2i and then like minus 2 plus I, minus 2 plus I, plus 2 plus I. Okay, I squared is minus 1, so minus 2, minus 4 I believe. 2i, okay. So that is our residue at z equals minus 2 plus I. So now, like that expression, okay, whatever. 2 pi I times by and our expression here. So e to the minus 2 minus 4i. Bro, I have like the worst memory. 2i. Okay, and then 2i, those are gone, so like pi e to minus 2 minus 4i. Okay, so this like expression, like I can't really say real integral, but like it has like real bounds at least, but like it's still like a complex function kind of. That expression is equal to this. So like if I want to like actually write this out more better, I guess, e to the minus 2, and then, okay, so like the cosine, I sine, whatever, cosine 4 minus sine 4. Yeah, okay. Or I can like, I don't know, I can say this, pi squared cos 4 minus sine 4. Okay, now finally, what we can do is just equate the real and imaginary parts. So like the real part of like the left side, that was equal to cosine of 2z. Z squared plus 4z plus 5. And then plus I, oh sorry, I forgot an I in all of these. Okay. I of minus infinity. Sine of 2z, z squared plus 2z, 4z, plus 5, dz. Okay, so what that means is just equate the real and imaginary parts. So like this part is equal to this, okay, I'm not doing that. This part is equal to pi e squared of cos 4. This one is pi e squared of, okay, minus sine 4. Is that correct though? Yes, okay. So, yeah, that's basically that. Because basically just like force the circular arc to be 0 and like we only get the actual expression that we want. So that's the basic idea. Yeah, these are a bunch of typos here. Okay, that is it, Jesus Christ. How do I take this off? Nah, what the hell, I can't take this off.
Must be the flag. Okay, thank you, Thomas, for that. Okay, I think everyone can hear me okay. So in the interest of everyone, including me, I'll try to make this section relatively brief, given that this is meant to be 3 hours and we only have an hour left. So now we're moving on to the vector calculus half of the course. Like Jerry said, for those of you that were here at the start, we are only going to be looking at the last 7 or so weeks, last 4 weeks and a little bit of week 5, just to lead into that, because you can review the midterm crash course for the first 5 weeks if you want to. That's also on ELSOC's YouTube channel. Okay, so we'll just we'll go through integration to start off with, which comes from week 5, and then lead into week 7, talking about everything else we'll cover in this first topic of integrals. So we'll eventually get up to our main new topic, which is a new concept from week 7, which was the change of variables formula, and then I'll go through after that the week 8 content, which is mostly line integrals and Green's theorem. Okay, so starting off with this, we are looking at Fubini's theorem. So basically what Fubini's theorem, you don't really need to know the precise details. All you need to know is that when we have a rectangular domain that we're integrating over, all we can just do is say we can do the integral iteratively, as in we integrate over fixed x, our function, as if it was just a function of x, and then integrate over x. Okay, so we'll see an example of that, and you can also see here you can do it the other way if you want to. I think example best motivated. So in this example here, we want to integrate this function y sine xy over this region. So we could say that this is equal to the integral from 1 to 2 in our x, and then 0 to pi y sine xy. That would be dy dx. Okay, so we're integrating with respect to y first, but I'm noticing that's probably not the best strategy, because then we'd have to do integration by parts, which I am not in the mood to do right now. So in the interest of being efficient, let's change it up like Fubini tells us we can do. Little magic trick in the spirit of his name, I suppose. Similar. So let's do x first, then y, and so we can do the x integral first. This gives us, the nice thing is the y will cancel out. We go to negative cosine, unless I've completely forgotten my year 11 math. Y here. 2, 1 dx, and then all you're just left with is a, you sub in for the x, the 2 and the 1, this should be a dy, sorry, and then you're just left with a standard trigonometric sum, this one here, which I'm sure you know how to evaluate. Oh, it turns out it gives 0 at the end. Okay, interesting. So that's what we do there. And then we also may have the situation where we have slightly more complicated regions. For instance, if we have a region that looks something like, I guess, this, where we have a phi 1 at the bottom as a function of x, and a phi 2 as a function of x at the top, but we have, it's a like this. So we have a range of x values that we can go over, then our y values that vary depending on what our x values is. So this could be our region that we're integrating over, something like this. What we can just say is we can do that same idea again of doing the iterative integrals to find what the integral of this function is. Okay, and likewise, we'll look at an example of that on the next slide. So first of all, we just want to plot out what this region here looks like. We're told it's bounded by the line y equals square root x. It looks something like this. Y equals to x, that would be intercepting it like this. And then y equals x over 2, so that would have half of the gradient. So that would be down here. Okay, have I made a mistake yet? Don't think so. Yeah, looks something like that. Okay, so I suppose if we extend this, I would see that since it wants the area bounded by those three, then we have to look at the area that has these three colors as the different sides, so that would be this. First thing we want to do, obviously the interception point, one of them would be 0, 0. Second interception point we see is from green and red. Which one did I make green? This one. So where x over 2 is equal to square root x, x squared, I guess we could factorize. So square root x over 2 minus 1, so x equals to 4, it seems. Okay, so this would be 4 and then 2. Okay, so what we then need to say is that we can, this looks something like what we talked about here. We can make the integral into an expression that looks something like this, depending on phi 1 and phi 2 that we choose. In this case, we can kind of notice that we have two different upper bounds in terms of this, where's my laser point? This top part, this top bound, this top edge, you could say. But our bottom edge will always be this line, x over 2. So what this integral would look like, it would be integral over, this would be 1, 0 to 1 of x over 2 up until this blue one, x, so we said blue one was x, and that would be just our, what was our function? Since we just want the area, we would just be integrating over 1, dy dx, and then plus the other part of the integral, which would go from 1 to 4 of the other function. So this is now our bound here, be square root x at the top, our upper bound for our phi 2. Our lower bound would be still x over 2, and this would be 1 dx dy. I won't evaluate that, but that should be correct. That is what I've got here. And yeah, you can see through the details. By the way, if you have any questions at any time, please let me know. Likewise, if you're watching online, please let me know if you have any questions. Yes. Yes, question.
Yes, sorry. How do we choose which bounds are which for the integrals?
In terms of, are you talking about how we split this up into two terms, or are you talking about how we chose the upper and lower?
How do we choose, the upper and lower bounds? How do we decide which one's x, which one's y?
Like the top or the bottom, or?
Or which is the inside integral and which is the outside integral?
Oh, okay. So let's look at this one. So in this case, we're looking at this part of the area, right? So in this case, we notice that that area, in terms of its x, it goes from 0 to 1. And then depending on what x is, the y values, they are above this line and below this line. So we say the y values are bounded below by the green one, and above by the blue one. So we would say we're going over, like intuitively, we're going over all x values from 0 to 1, and then we're bounded between these two. So the reason why I chose x and not y here, I suppose y could also work, but since we're given functions of x in terms of our y values, it's just easier to work that way. You could also, I guess, flip it around if you go from your 0 to 1 in your y, that should work similarly. Just might be a bit more finicky. You could rearrange this like here would mean x equals to 2y, so you have a bound for your x in terms of y. So I guess for this same area, if we're trying to find this same area in terms of a, call this I1, this I1 would be integral, this is also 1, so this point's 1, 1, so we would want to go over 0 to 1 in terms of y as well. This green is, actually our upper bound would in that case be this line here, which is x equals to 1, so 1. Our lower bound would be this blue line, which is x equals y, so we could put y here, and we're integrating dx, then dy. Okay, does that make sense? Okay. So let me know if anyone has some more questions as we go. So in terms of change of variables, we'll go through change of variables more formally. First of all, in terms of integrating in 2 dimensions, one particularly nice change of variables is when you go to polar coordinates, where you change your dx dy to r dr d theta, and we make these substitutions where we're effectively saying this point is cosine theta, well, this is theta, this is the length, so we can represent any point by these coordinates. Okay. So it just might be more convenient to integrate over, because what we may have, like with this example, is our domain that we're integrating over can be better represented in terms of polar coordinates, because in this case this is the same as saying that in terms of polar coordinates r squared is less than or equal to 1, and what this says is that our theta, since we're in the first quadrant, this denotes the first quadrant, x and y are both positive, theta, our angle, would be between 0 and pi over 2. Okay, so we can make that substitution. In that case, this integral, we call this I, would become integral from, this would mean r is between 0 and 1 because r is positive, that is between 0 and pi over 2, and this would become r squared cosine squared theta, r squared sine squared theta by substituting our x and y, and we have to then times by the r because we need to make this substitution of dx dy equals r dr d theta, and we're going to put d theta first, then dr. Okay, and you should be able to see that's what we do here. So we get r, sorry, this should be cubed here. We get r to the 6, our cosine squared, sine cubed, and the rest is the same. Oh, in this case I just put the dr and the d theta the other way because I have the integrals like this. They just flip it around because Fubini says we can do that. Everyone okay with that? And you can see the computation here. You can follow the steps and see that it results in 2 over 105. Okay, so moving on to triple integrals, those are quite similar in terms of what we have to do. In this case, we're working in the first octant, and we are given this equation which bounds the other side of our volume. So effectively, it's a bit hard to visualize, but if you look at the case where we just have this in, say, 2 dimensions, this is basically going to be, this would be a line. If we like fix a z value, it's effectively a line. So it looks something like this. So our area would look something like this. If we extend that to, try to draw it again. If we extend that to the 3rd dimension, what that looks like is we have this type of tetrahedron that bounds our area like this. So area is like this whole area beneath it, I guess. Okay. So in terms of finding our bounds, since we just want to find the volume, like our f is also equal to 1, so we're just integrating the identity function. I suppose since we know we want ABC all positive, the maximum, I guess if we integrate over x, let's look at integrating over x. So again, we can draw back that example we had earlier where we had, if we look at the x and y plane first of all, let's say z is equal to 0, so let's ignore z. If we look at the x and y plane, we would see that this is, as I said, a line where we can go from, our x-intercept would be a, and our y-intercept would be b, like this. Okay, so that's, I guess, our domain, and that would mean that our volume, we would start off going from 0 to a, and then, I guess, supposing z is still 0, we can say this is 0 to 1 minus x over a, I believe. Oh, b times that. Just saying z0 rearranging for y gives this as our upper bound. And that's effectively saying we have like coverage of this whole region here. Again, we do have the z part playing into the mix. So now if we suppose z's non-zero, then we have a little bit of a tighter bound on what z can be. So if we imagine this is like the projection of our volume onto the xy plane, you'd have your z-axis going up top, and there'll be like this point up here directed down. There would be a restriction on what value of z would be depending on where our x and y are. So we would say the little trick is you can just pretty much solve for the interception points here. We want z to be greater than or equal to 0, so that's our lower bound at the very least, so 0. And then it will depend on what x and y are. We can rearrange this equation to find z in terms of x and y at the current state, which would be c times 1 minus x over a minus y over b. 1 dz dy dx. Okay, so I'm just going to check that's correct first of all. Yep, so you can see the computation, you can go forward there. I think I did miss a little bit of explanation with that, I suppose. So as I said, your z is pointing up like this. You have a little, your tetrahedron type shape. Depending on where you are in terms of your x and y plane, say we're here in terms of x and y, there's a certain, like, this is your boundary, I guess, the surface here, which is described by this equation. That's the maximum z you can go up to. So hopefully that sheds a little light on it. But in the interest of time, I will move on. Similarly, we do have cylindrical coordinates. I guess easing us into a third dimension a little bit more. That's really the same as polar coordinates, but now we just have a z. Well, we keep z the same, but we have x and y represented in terms of these polar coordinates. So it looks like a cylinder. If you look at the z going up, and then you have your radius of your cylinder and your angle around the cylinder. So that's our change of variables. In that case, we can do integrals like this, where we can substitute in cylindrical coordinates, this would become r squared. And as we said, we can substitute that in, so there'll be another r here. In terms of this boundary, we can represent this as z equals r squared over 2 for this boundary. Over here, we can say that this is r squared equals 16, so we have two nice little conditions. There's no real restriction on what theta is, so we could say theta is between 0 and 2 pi, so going around the full revolution, because I don't see any other restrictions there, and I think that should be good. So we go from 0 to 4 in terms of r, and then for our z, we would have that as a function of r as well. So I won't write the whole thing up. I'm pretty sure I have what I have in mind. Yep, so this is what I had in mind. In the interest of time, you can try to work through the tiny details I just skipped over using similar ideas to what we covered in the previous examples. But since I said, yeah, theta is not restricted, we go through every theta, then we go through all the r values, and then we look at what z is as a function of r here in terms of what values do we allow. And this does mean that we go starting from the lower bound of z is equals to 0. So essentially the tricks, if you're unsure how to visualize it, all you can really do is just consider the bounds that you have, like say z equals to 0 is like one of your bounds, and this one's another bound, so it's between them in some sort of way. So if you just pretty much just chuck those into the bounds of the integral, then it usually works out pretty nicely. Okay. Any questions? Okay. What is... Okay, I was scared at the touchscreen almost. Okay, I think we're good. Yeah, and that's your final answer if you want to have a look at that. Okay, so a little bit more tricky, we can look at spherical coordinates, which have this rather ghastly change of variables formula. But you can visualize this as your rho is now your radius of your sphere, effectively. We don't use r to not confuse it with cylindrical coordinates or polar coordinates. But you can think of having a specific r in terms of this, your rho sine theta in terms of your x and y plane. You can think of that as your r. So what we say is that rho is the radius, and this phi here is this angle from the z-axis to your point, the line from your point to your origin. And then if you consider the x and y plane with that, you get a radius, if you like project that downwards onto the x and y plane, that is rho sine phi, and then you can break that into your x and your x and y, I suppose, yeah, by looking at the angle that makes with the y axis, this theta here, and you can do your basic trigonometry of r sine theta, r cosine theta, similar with polar coordinates to get, combining that, your r is rho sine theta, so it becomes rho sine phi cosine theta for your x, and similarly for your y, whereas z is more simple, it's just your, in this case, rho cosine theta. Okay, so if that makes sense, just to revise, our change of variables is rho squared sine phi, so we'll use that here. So we have a cone equals to square root x squared plus y squared, and we have this sphere. So the first thing we want to do, basically, because this looks a lot like spherical type geometric structures, we want to represent this in terms of spherical coordinates, because that'll make it more easy to find the volume. Again, we're using the function 1 that we're going to integrate over here. So in terms of this one, this would be rho squared, because that's the radius, is equal to 2a rho, and then it'll be, what we say, cosine phi. So this equation says that rho is equal to 2a cosine phi. This one here says that rho cosine phi is equal to this radius, which we said was rho sine phi. So we have two conditions here. I guess we have sine phi over cosine phi is equal to 1, so phi is equal to pi over 4, because that's tan is equal to 1 when the angle is pi over 4. And we have this other condition. Is there anything else we need to look at in terms of our bounds? That should be good. So if you try to draw this out, I guess if you look at only your r plane, so this is r, this is your z, what this cone looks like is z equals to r, so that's this, and then our sphere is r squared plus z squared equals 2az. So that's a sphere centered at A. You can write that as r squared plus z squared, or z minus a, if you complete the square, should be equal to a squared. So radius a is positive, I think we're allowed to assume. So we can put a here and say that the sphere would, so yeah, it will be intercepting here because it has radius a, and then it'll be up here, so some sort of circle looking like this. I think that looks good. So we want to find the area. Okay, so we want to effectively find, since this is our cone, you can imagine this in 3 dimensions. If you rotate it around your R, we want to find, it looks like this area here. Okay, so that's a little bit of a simplified drawing. So basically we're going from phi from 0 to pi over 4. We're allowing, I guess, any theta angle, because I said we can rotate it around, and our z would depend on what, our rho would depend on what phi is like this. So rho would go from 0 to this, looks like. Okay, so you can see that in action. You can see the calculations for what I kind of just intuitively walked through. Yeah, so that's exactly what I meant to describe right there. Okay, so you can review that in your own time, but that, if you go through it, is going to provide this as our answer there. Okay, any questions? Okay, cool. All right, so this should be one of the last parts here in terms of the integration part. So we have this change of variable formula. I know this is a bit technical in the way it's represented here. The long story short of this is that when we have a change of variables, such as from our regular coordinates to say polar coordinates or spherical coordinates, then what we do is we use the Jacobian that you would have seen in the first half of the course for that transformation. We take the determinant of that and we basically multiply that in. So I guess the tricky part, and what this is all saying, is that you have to be a bit careful as to which side you put the determinant in, but hopefully it becomes relatively intuitive. The way you can think about it is determinant is like the, well, first of all, it's the volume of the parallel pipette if you look at R3, so it's how much volume stretches once you do that transformation. So you would think that the determinant is also thought of as the derivative, so it's how much your output changes with respect to your input. So it's like you're doing your, when you do your U substitution in your regular calculus, it's like going from, let's say you have U as a function of X, you're looking at some F dx, that would be equal to the integral of F du times, what do we have to put? We have to put dx over du usually, I believe. Yeah, because we kind of have to make it back to that dx. So this would be 1 over u dash. Or in other words, you could have u dash here, and then you're putting it here, I suppose. Okay, if that is good. So we'll look at an example in action for that. So we have this not very nice function where we have this region omega with bounds looking like this, which aren't very nice either, which begs us to kind of use a new coordinate system because there's a bit of similarity in how we're representing each of these bounds in terms of our x, y here and our x squared here. So it kind of begs us to use a new coordinate system where we're maybe going to make, don't remember exactly, but we want to use this as a new variable, and then, oh yeah, the y squared minus x as a new variable to represent this. And you can see by this, that's another way to represent this area that we are integrating over. So if we make this first function of x and y, our u, our v, and this second one, our u, then we can represent this omega as the uv in R2, such that 1 is less than or equal to v, so less than or equal to 2, and then u is between 0 and 1. So we have nice bounds for u and v there. Okay, so that makes the area we want to integrate over much simpler. And we can also say that this part here is going to be, that's v here, and what this looks like is going to be something we can make from this, I think. We'll look through that in a second though. So in terms of the Jacobian, as I said before, we want to find that. So since we have u and v as a function of x and y, we can find the Jacobian, the change in u with respect to x and y. You can do the calculations in terms of partial derivatives. It provides this in which you can find the Jacobian of, well, we say f here because what we need, instead of just the Jacobian of g, the regular transformation, we need the inverse, because we want, like effectively we want the change in x, y with respect to the change in uv, so that we can kind of simulate integrating over x and y in terms of u and v, because what we want, we know we can write our integral. We have this integral here, that's like our I. We have I is equal to our integral over dx dy of f. We want that in terms of du dv. And you can kind of see that these cancel out, and it's like the same as the dx dy. So that's the intuition behind what's going on. So that's why we need the the dx over the dxy over duv. So we take the determinant of like the inverse of g, which is the same as the reciprocal of the determinant of f, which turns out to be, if you do the calculations, x plus 2y squared. And luckily enough for us, we first note that we're integrating over a area which x and y are both positive. And so this is just going to be positive, so we don't really have to care about the absolute value. The other nice thing is that when we substitute this in, if I'm allowed to draw, is that, remember before we had this x plus 2y squared that I didn't really know what to do with before, but notice it just cancels out with this here. So I guess they were giving us a purposely nice integral to work with. You can see then we can do the calculations, and it's quite simple to evaluate this integral, even though the original integral was quite complicated. Okay. All right, so we'll just keep going. So we'll briefly walk through this. So we just need to know what that line integral is and how to work with Green's theorem. So what a line integral is effectively, if you're familiar with physics, it's effectively the work of a force. So you can imagine this function is a vector value function going from Rn to Rm, where what we're doing here is we're effectively saying ds is like we have some sort of curve, so this is a curve C, and our ds is like the tangent vector along the curve, ds. Okay, and what we're doing is we're finding the dot product between that and our force. So effectively, what we're measuring is how close the force is to the direction of the curve, so work done across that little path. So that's what we call a line integral. And if you parameterize that, you're effectively saying that it's the force dot product with the tangent vector to your curve. So you're parameterizing the curve with this c of t. This is the tangent vector. You can write that as c dash t here, right? And we're integrating with respect to t. Okay, so this is like the velocity here effectively, and this is our force, so dt. And if you're familiar with physics, that's the same as like the like velocity times dt is like the change in displacement. So that's the same as this we had here. Okay, that's another like change of variables trick we talked about with the previous slide. Okay, but you don't really need to know all the technical details there, just that if you want to compute a line integral, you can use this nice formula here. And just remember, that this curve that we're dealing with is oriented, meaning there's a specific direction we have to go in, so you can't like integrate over the opposite direction like this. So you need to make sure all parameterizations go in the correct direction. Okay. Right, so what we need to look at now is, if we have functions m and p, we can write this, we can write what I'm going to write here as this, I would say. This is effectively the same as what we looked at on the previous slide. You can imagine it like this. This is the same as this is the same as talking about the ds from before. This dx is, if you're working in R3, becomes your dx, dy, dz, and this would be your value, the function f, which will now break it into a function m, n, and p for each of the components. Okay, so what we can do, like we talked about on the previous slide, we can parameterize the curve into its x, y, and z coordinates, and we can take the derivative and then dot product that. So we're effectively summing up the m times the derivative of the x, like we talked about on the previous slide, and so this is just expanding out the dot product there to get the whole integral. Okay, so hopefully we have an example on the next slide. You can read intuitive things like the work here, but we have an example here now that we want to look at. Personally, I like to always draw this, or write this as the dot product version. It just makes it easier for me to visualize. Since we're working on the unit circle, our parameterization would be c of t. I guess it doesn't give an orientation, so we'll take the standard orientation, I think. Did I mention the standard orientation? If it doesn't say, the standard orientation is going to be anti-clockwise, like with your complex numbers, because that's the positive in math, I suppose. C of t would be cosine t, sine of t. Since it's saying over the unit circle, we want to go one full loop. C dash t is equal to negative sine t, cosine t. And so this will become, we can see the calculations here. You can expand out the dot product. And in this case, it turns out to be 2 pi. Okay. If you find derivatives, you multiply that by x and y. X is now cosine, so you get cosine t squared here, or do you? Oh yeah, because you have your dy, and then your dx here. Okay. Did I make a typo on the previous slide regarding that? Oh, yeah, okay, so in this case it should be negative y and x here. Yeah, okay, sure. Alright, and some just properties of line integrals, you can split it up. They are linear, so if you have two different functions, you just take the sum and bring out the constant. If you reverse the direction of your curve, then you just take the negative of the line integral, and if you have your curve as a composition of a bunch of different sections, you can just split it up into all those different sections, like we do with integrating in our regular R into different intervals. We split up the interval into. So here we have a little question on that. So we have a function that's just constant 1, 1, 1, and our curve is joining the points, not the origin, but 1, 0, and then 0, -1. I'm assuming this order, 0, -1, down here. So this should just be 1, 0. Yeah, so it's just going to look like this, so diamond type shape. So we're going this direction. And since you can kind of intuit that since this function is constant, the integrals over every side are just going to cancel out effectively because you just sum up effectively the vectors, and or you can like argue here that since you split it up to the different components, and if you flip the direction, it will become negative. Say this side would cancel out with this side, and likewise this side would cancel out with this side, so the overall integral would become 0. So 0 here. That's what we argue here. So this is just motivation for what we call the fundamental theorem of calculus for line integrals specifically. So this is the idea of an antiderivative, but for line integrals. So this only works for functions that are conservative. So a function is called conservative when there is a scalar potential phi such that f is the gradient of phi. And so if that's the case, we can effectively do our fundamental theorem of calculus and integrate by taking the antiderivative, which would be phi in this case, and evaluate the integral at the different endpoints. That's to say that the integral is independent on our choice of parameterization, or sorry, not parameterization, but rather the line that we take from A to B. So it doesn't matter. Okay. Yeah, so only dependent on the endpoints. So we're looking at an example of that here. So we're given this function. It's going from A to B. So you can do the calculation explicitly, where you parameterize this curve by, say, the curve would be C of t is equal to t, 2t, 3t, where t is between 0 and 1, and you can compute it because f is a function of x, y, z. You can find those in terms of t, so you can do it like this, where you can find the integral to be 11. But using what we just learned, we want to maybe do that in a bit more of an efficient way, because this question does hint that this f is going to be conservative, because it says show that the integral is the same regardless of the path taken. So we can do that. We can show that it's independent of the path taken by showing that it's only dependent on the endpoints, by showing that f is the gradient of some scalar phi. So we can do that by saying like dx by d, sorry, d phi by dx is equal to this y. So looking at this x component, likewise d phi by dy is equal to x, and then d phi by dz is equal to 2z, and you can solve this equation to get xy plus z squared. If you look at this is similar to, I think, working with your Cauchy-Riemann equations, or with harmonic functions, I believe. So it's similar in logic to that. You have these three differential equations. You can solve them. Say solving this one gives phi is x times y plus a constant, a function that depends on f and z, and you can likewise work with the x. Eventually you find that the function is the one I spoke about earlier, xy plus z squared plus some constant, and so that means that the work that we do is the same no matter what path we take from A to B, as long as we have the same starting and ending points in our path. Alright, so last thing we want to look at here is just going to be Green's theorem, which I'll just briefly walk through in the interest of time. So Green's theorem, the short version of it is that it's the two-dimensional case of Stokes' theorem, where we have this kind of ghastly expression over here, which is saying that this, which represents the path integral around the boundary of C, so C would be, if we draw it out, we don't really need that, but we have C as some sort of, the boundary of some sort of region, C. We're taking this integral here, that's going to be the integral over C, so this part here, whereas D is the integral over the area enclosed by C. So what is effectively saying, since this is the two-dimension version of the curl that you learn about with Sid, or I guess revised with Sid, this is representing the sum of all the curls, like the measure of how circulating your vector function is. In this case, your vector function is f equals pq. It's a measure of how much the function f is circulating around a particular point. If you sum that up across the whole area, you just get kind of this circulation on the boundary. So like the sum of all the f's on the boundary, like your work integral, your line integral across the boundary, which is what this is. Okay, so that's kind of the intuition behind what's going on. Again, we take it to be anti-clockwise as our standard positive direction. But this is just the formula here. So if you don't bother remembering the intuition about it, you can just remember the formula. But if you make that link between this and then Stokes' theorem later on, it's much easier to remember, in my opinion. So we'll, of course, of course, this question is going to be about using Green's theorem. No spoilers there. So we have an expression that looks something similar to the setup here. And we are saying that C is the unit circle. So the boundary of that would be unit circle, and sorry, the interior of that would be the unit ball. So in this case, we're looking at, this is where we're trying to integrate over. The interior would be inside of there. Okay, so we want to turn this into some sort of integral over this blue domain of this expression. So we want to find what d partial q with respect to x is. So we can find that that is going to be partial of this with respect to x, so x squared. And then minus that to partial p with respect to y. P is here, so that'll be minus negative y squared. And then it'll be dx dy. Okay, so this turns out to be very nice. It's just the integral of the domain of x squared plus y squared dx dy over the unit ball, which we can use polar coordinates to find quite nicely, because this would just be r squared, and it'll turn into r cubed times the r d theta. And where did the 3 come from? Am I tripping? That is an excellent point, yes. When you differentiate x cubed, it gives you a 3x squared, likewise with negative 3, negative y cubed. Excellent point, thank you, Sid. Cool. I think he's prepared for his section. Okay, so you could work through the rest of the details there. Again, with the interest of time, I think I will hand it over now to Sid. You can find the final answer here. You can review this in your own time. We'll try to upload these slides, but hopefully I just want to give you the main intuition, because I'm pretty sure you have a question bank you can go through anyways. More important that you know the intuition behind what's going on. Okay, so sorry for leaving you such short time, Sid. You can go, so I guess we don't need the room until I guess 1:30, so you can go if you want.
Yeah. Okie dokie. So, vector fields and kind of the rest of the theorems we'll quickly go through. Just before we actually kind of intuitively think about what a vector field is, here's a kind of neat diagram. So it's basically just, you have a bunch of vectors at any given point due to kind of the makeup of the field, and that is just presented with a list of vectors. And primarily we'll be dealing in R3 and R2, so most of the time they'll just be 3 vectors or 2 vectors. And the gradient of which can just be found with this expression. So once again in R3, it'll just be df dx, df dy, and df dz. And yeah, so divergence is one of 2 very useful calculations we can make about vector fields. It's basically just the flux of P. So basically to direct how much, what's the vector looking like at that point, which is basically just, the gradient of the vector field dotted with, some scalar function. So we're trying to find what the gradient is at that point. And it just ends up being this in 3D, in R3, when it's R2. We'll talk about that when we come to curls. But basically, here is an example. If we try and find the gradient of our 1 on R here, R is just the quadrature of this function, which is going to be x squared plus y squared plus z squared. And that is going to be 1 over that, so this expression here, the negative to the power of negative 1.5. When we take the derivative, we have this lovely function. Hopefully we know how to do that. And then, yeah, all we have to do is dot that with our r. So we don't really have to do anything here. We just need to multiply it by r. And yeah, here we go. It's minus r over r cubed. And the next concept is the curl. So the curl is kind of the cross product alternative to the divergence. It's basically how much the vector field curls or like bends around a point. Swirls is the word they use here. So yeah, instead of using dot product, we'll be cross producting. It doesn't really matter. Like I'm personally not a huge fan of this notation, but this is kind of like the result every single time. And when f is a 2D vector field, you just set f3 as 0, and it's pretty straightforward from there. But yeah, let's have a look at an example of how to calculate our curl. What is that? The 3, whatever. That doesn't really matter. Oh yeah, and as always, anti-clockwise is our assumed condition. If we're doing it clockwise, or as later on we'll be looking at normals, if normals are pointing at the other way that we like it to, you'll just be out by a negative. Just be kind of semi-conscious of that. Okay, so as always, our gradient is just simply our dx, dy, dz when we cross product it with our I, j, and k coordinates. So the first thing you typically want to do is just write that as a vector field rather than the I, j, k coordinates. Like that's a lot more intuitive, and then especially when you like cross it like that. And then, yeah, hopefully we all know how to do our cross product. This way, this way, this way, this way. And surprisingly, it comes out as 0. And when it is equal to 0, we call that as a irrotational. Okie dokie. Any questions about divergence and curls? I think those are pretty straightforward. Okay, next up, we're going to be dealing with 3D surfaces and how to parameterize and integrate those. So they use z here, but normally we use this phi. Basically, it's just taking some input of u and v, and we give it a third dimensional quality to it. In this case, we can take x and y, and then our phi there would be z. And we can take two tangential vectors from the way we parameterize, and that is just deriving it based on u or v. So in this case, we can derive that based on x and y, and we'll get kind of two vectors, if you will. Maybe blue wasn't the best color for that. And then to find the normal, we just have to cross product those two, like how you find the normal back in 1a. Shouldn't be a huge problem there. And basically we can do a very similar thing as we did with the path integrals, and we'll dive into that now. So we'll be dealing with some properties, so like simple, smooth. So smooth is just like the first derivative of all three vectors need to be continuous. It's kind of, I don't think they'll give you one that's not smooth, but that's what it means. So here is what the surface integral would look like. So it's the function based on our parameterized one, and then multiplied or like dotted most of the time with our normal, or our normal in quadrature. And this ds is terrible to work with, so we'll change the surface to a 2D domain based on du dx as well. And that is a very similar thing. Okie dokie. So here we have an example. Consider a surface S given by this parameterization x and y, which is pretty easy to work with. When we differentiate like x, y, x squared plus y squared. When we differentiate this in to x, we get our tx. When we differentiate to y, we get our ty. When we cross product this, we have our normal. So we want our normal in quadrature. So square everything and put it under square root. And then our area is just simply what we said before. It's the double integral of that based on our x and y coordinates, which after we compute it, it'll be something like this. Any questions about that? OK, great. So that was when we're dealing with a scalar, like so. But we can also sometimes be dealing with a vector field. And it really doesn't make a difference. The difference is just you need to dot it with your normal vector first. And the key here, it was maybe somewhere here before, but yeah, make sure your normal vector will normally be pointing outwards. If it's pointing inwards for some reason to your surface, you'll be out by negative. So maybe check that if you are worried, but most of the time I do not think it'll be an issue. Yes?
The easiest way to check that would be just draw a quick diagram.
Yeah, I mean, I think try and draw a diagram if you can. That'll be pretty damn difficult. It kind of depends. So the example we have down the bottom, it's just a circle, so like a unit circle. That'll be pretty straightforward. But if it's like a very difficult parameterization, I think most of the time when you do, it will give you a positive one just because they won't make it too difficult. But if it's a very difficult shape, yeah, it'll be very, very hard. Yeah, and hopefully they'll give us like simple enough shapes like a ellipsoid or a circle or a sphere. Sorry, not a circle. Okie dokie. Sorry, scroll down a little bit too much. And just before we move on, here is the flux integral formula. So this is just how to calculate like the flux across a region. So like a path integral along something, and then yeah, the vector field dotted with the normal. So just the vector field going in the direction of the normal, basically, is the flux. Yep. OK, so Stokes' theorem is useful in a way because it's the pseudo equivalent of the Green's theorem. So if we take this, if you imagine it's like a 3D shape, and then we have like a 2D encirclement of it, and we try and find like what that is, like when we try to integrate it, that could be pretty difficult. However, Stokes' theorem just tells us that that is equal to the, so that is our curl. Yeah, the integral of the curl over the entire 3D region, because everything inside would be cancelled, and it's just the edge factors that take into consideration. So yeah, here's a visualization if you find that helpful. Yeah, so if we try and have a look through this example, we have a surface here and a vector field. First, let's try and find the curl, which is just our gradient crossed by our vector field, which gives you this. And then next, we want to try and get our parameterized version of the surface, which we can write. So x plus y plus z equals 0. So you can just write that as x, y, and well, they write it as minus x plus y down the bottom, but you kind of get where that comes from. And then to get the normal, once again, we derive that based on x and y, which gives you 1, 0, negative 1s, and 0, 1, negative 1. Cross product of that, 3 1s. Once again, don't forget that you need it in quadrature, you need it in unit length, which gives us that as our sort of normalized vector. And then next up, all we have to do is we just to dot our curl with our normal here. And then we, so this like transition is just the same as our surface integral here. So instead of the .ds, we dot it with the normal, and we change the ds to du dv. So that's how we parameterize it from 3D to 2D. Yeah, and then we can take the 1 on root 3 out, and it's just 1, so you just kind of add these 3 together. And then, yeah, all you have to do is do the integral, which, for the sake of time, or for my own sanity, I won't go through. Yeah, okay. Next up, we have the divergence theorem, which, so before with the Stokes theorem, we were looking at the application of curl in a 3D space and vector field. Now, divergence theorem is, surprise, the divergence in a vector field. So basically, if we are looking like concerned about a region at all, like this applies. So C1 means continuous differentiable. Once again, hopefully it is. Otherwise, what's the point of the question? So yeah, if you want to double check that, you can. Yeah, and it's typically helpful to go this way. Yeah. Let's have a look at this example. So they say a unit disk, but it's a unit sphere plus its entire interior. And yeah, let S be the surface oriented so that the normal vector points outwards. Thank you. And F be a vector field defined by that. So we want to calculate this, which first we should find the curl, which we do just by, once again, doing, sorry, not the curl. First, we want to find the divergence. Yes? Is that the flux? Very great question. Let me have a look. So the flux is a closed integral with to normal, and that is a integral across the surface, a 3D region. No, it's not equal to the flux. So this is just like the divergence within that region rather than the curl within that region, I believe. Yeah, okay. Let me think about that, and I'll get back to you after I finish my part. Yes?
Would it just be like, if we're integrating over the surface, would it just be all the normals as opposed to on the surface as opposed to the normals on?
All the normals to the surface. Sorry, could you just repeat that question, please?
I'm just trying to think about the relation might be.
Oh, yeah.
I'm probably wrong.
So, I mean, okay. Bounded to the surface, then yeah, so you're dealing with the divergence across a surface. So I suppose it is similar in a way to the flux, because the flux is just across the normal in a path. But yeah, I suppose this in a way is dealing in a 2D sense, which is why I got confused. Maybe 3D. The divergence across the region. Yeah. I think that there are some. Yes, I think that this is precisely the flux. Yeah, because it's a divergence across that surface on the field, and yes, that of the shape, which is exactly what the flux would be. It's just, yeah, this isn't really parameterized to a normal vector, so there's no direction to it. Okie dokie. Yes, as before, divergence in this case pretty straightforward. We just derive the 3 vectors given by our vector field, which is equal to 4, And then we just apply that to our region here. So our 4, like if that is equal to 4, we can take that out. And then that is just the region of the entire 3D space, which you might be tempted to use polar coordinates for, which I didn't really cover what that space, just because we're looking at a sphere. But also you can just say it's a sphere with radius 1, therefore it's going to equal to 4 pi on 3, and it's just going to be 16 pi on 3 there, from there onwards. Yeah. It is a flux. It is a flux, yes. It's my fault. So, it's slightly different notation, but yes, it is effectively flux. Yeah. Yes. Okay. Well, good. Thank you very much for coming, and good luck in your finals.